Hey everybody, tonight we're debating whether or not space exists, and we're starting right now. With Flat Earth Aussie's opening statement. Thanks for being with us, Flat Earth Aussie. The floor is all yours.
Cheers, James. Thanks, Tom. I've written out a little bit of a spiel, but I must say I also bought my own hand grenades. But I'm vegan, so it's a vegan hand grenade, so maybe it's the wrong thing to bring to a knife fight, but here we go. I must say it's an absolute honour to finally meet such an esteemed opponent. I'm actually quite amazed that this discussion is finally going ahead. Big respect, first of all, to James and all the moderators who make this unbiased, non-partisan platform possible. And secondly, to my highly decorated armchair philosopher opponent, Sir Thomas of Jump. While he may get to prove his ability to stand on his own 2 feet, he may yet to prove his ability to stand on his own 2 feet, figuratively speaking, on any topic yet to do with the spinning, open-air, organic, pear-shaped spaceship twirling and whirling at multiple speeds and directions through the vacuum of infinite space, kudos must be given to him for reattaching his butt after having it recently handed to him on a shiny metal platter after a recent encounter with a bloke from Hawaii called Dave. Today's topic, of course, is whether or not outer space is real, most especially as we currently tend to think of it according to current mainstream, which is to say, Hollywood consensus. There's no argument that real tangible gaps exist between real and tangible objects, though I do have questions for another day about the alleged space between the particles that real and tangible objects consist of, that of atoms, which hypothesise that even real and tangible objects are 99% empty space as well. I'll go with the consensus that real solid objects, for the purposes of this discussion, are real solid objects. What we're really simmering this cauldron of conundrums down to is the essence of the existence of outer space, specifically that vacuous state that's been indoctrinated into our fertile minds all the way from the crib to the hallowed halls of higher indoctrination, where we infused by degrees, sometimes with honours, just enough knowledge to make each trained monkey useful in its own specialised compartment. I know, I digress. Please, not for 1 second am I suggesting these learned people lack in intelligence. In that same breath, however, I will suggest that the best trained soldier or policy enforcer is better equipped to perform their roles thanks to a lack of intelligence and a willingness to follow orders. And so it follows all the way up the chain of command that every successful employee must be willing to compromise certain, shall we say, standards in order to enjoy a successful career. Those who rock the boat, so to speak, are often the first to fall overboard, accidentally or otherwise. So rather than delve down any conspiracy spiral, let us focus on physics, the very essence of the foundation of science. It seems quite ironic, really, that vacuum of space is the very antonym of physics, the complete lack of anything physical, the absolute metaphysical void. It must be stressed that the fantasy of outer space cannot exist, let alone persist, without the fabricated fantasy of the heliocentric globe and all that goes with it. First of all, placing us hypothetically on one of those tiny orbs of light we see in the night sky, spinning and twirling around in yet another of those tiny orbs of light, now supposed to be multiple magnitudes of our own sun, bigger in size, rendering even our own Son of God insignificant in the overall scheme of things, thus paving the way completely and utterly into the atheistic paradigm, rendering anything of intelligent design to be far less likely than the most amazing supercomputer capable of self-reproduction, little more than the accidental consequence of sheer random accident, freak beneficial mutations, and statistical consequence, given enough time, ironically associated with the wandering star god Kronos, otherwise known as Saturn, or as I call it, the great deceiver, the Lord of the Rings, Satan. The very topic of space being fake necessarily lends itself to multiple conspiracies and consequences that to simply list them off one after another will do no justice to any one of them, let alone my case in general. Yet I find myself wondering, like a country kid for the first time in the proverbial candy store, marvelling over the choice of juicy topics to sink my teeth into. I would dare say that each and every one is worthy of an entire debate in its own right, which, alas, forces me into a more generalised position, leaving the debunking of a million proven falsities of the space paradigm for another time, most especially those of NASA, not a space agency. Instead of disproving a negative, therefore, I'll focus on the more scientific method of proving the positive, specifically that we dwell upon the only plane of terra firma at the bottom of the known universe, which, by default, renders the entire concept of outer space redundant, extraneous to all the known and observable laws of physics. We know, for example, how the laws of physics apply to the field sports event we call the hammer throw. A heavy weight is attached to a tether, the athlete holds a handle at the other end and rapidly spins, applying maximum centripetal force to the hammer. At the moment it is released, it flies off in a straight line until eventually inertia gives way to friction and the density of the mass, otherwise known as weight, from the Latin term gravis, drops through the less resistant medium of air until being arrested by the more dense medium of the ground beneath it. It's no coincidence that the same person is described as standing with his 2 feet on the ground, or is well grounded, while the crazy person is said to be off with the fairies, which equates with pixie lights we see twirling and whirling in the empty space above us. Can you just imagine, therefore, a god like Thor descending to the physical plane and throwing a hammer so hard and fast that it just missed the ground in such a way that it continued falling to the ground, that every time it got close, it just missed again and again and again until eventually it ran into so much space debris that it formed into the moon? This is literally the closest you'll ever find from scientific consensus for the actual existence of our actual moon. So if that's the scientific consensus of just our nearest celestial body, can you just imagine how much more and more absurd it must necessarily get to believe that we do similarly to the sun as Thor's hammer does to our Earth? The sky clock we see rotating around above the stationary planar Earth remains constant, repetitive and predictable year after year, century after century, millennia after millennia. So to assert the positive position matched with our observations of the celestials above, we can posit that by definition of water level and the observable laws of density and buoyancy, that sea level is the mean bottom level of observable reality, and the various fluid gases filling some of the space above us loosely follow the same physical laws rather than defy them absolutely by clinging to an open-air organic spaceship whirling and twirling through a vacuum of space, let alone dragging Thor's hammer a constant distance away as it went. On the stationary planar Earth, when we apply laws of perspective and convergence, we view the model at the full scale with which it actually exists. It matters not how many rockets or A-bombs we send up in an Operation Fishbowl. We simply cannot penetrate above a certain height, despite all of the Hollywood fabrications suggesting otherwise. Could it possibly be a coincidence that one of the very first Hollywood productions was called A Trip to the Moon? The idea of space exploration has excited the imaginations of mankind since the beginning of time, so it is no wonder that the authors of fantasy have expanded to realms of science fiction to boldly go where no man has gone before, thanks to the genius hard at work in a Hollywood basement, the final frontier.
Thank you very much,
I'm done.
Flat Earth Aussie, for that opening statement. And want to let you know, folks, if it's your first time here at Modern Day Debate, we are a neutral platform hosting debates on science, religion, and politics. And we hope you feel welcome no matter what walk of life you are from. We host debates ranging from, as I mentioned, science, religion, and politics, including this political one coming up on the bottom right of your screen. It's going to be a juicy one. And so hit that subscribe button if you haven't already for many more juicy debates to come. And with that, Tom, thanks for being with us. The floor is all yours for your opening.
Yep. So space is a really simple concept. Like we can literally make parts of it by creating a vacuum chamber, sucking out all the air, and then poof, we got space. And we know this happens naturally because as we go up, there's less and less pressure. So the pressure decreases and continues to decrease and continues to decrease and continues to decrease to the point where we can't breathe. And we've literally just gone up high enough to the point where we can't breathe. And when we can create a vacuum chamber and put in even less air, we can know what's above that, and then less know what's above that. And in a vacuum chamber, when you put in air that doesn't like fill the container, or even it does, then the air will go to the bottom for some strange reason. The air will start to fall. The molecules will go to the bottom of the container. If you flip the container, it'll also go to the bottom of the container, whichever side is going down for some very strange reason. Which means that on the bottom of the container, there is some air, molecules, pressure, gas, and at the top of the container, there's nothing. That nothing is what we call space. Space is just the lack of particles. We know it's out there because, well, we've been there. We can see it. Rich people can get pretty close, apparently now. And we can demonstrate all of the celestial bodies pretty simply, the best one being the moon. We can demonstrate the moon is there in your backyard with a radio wave called this thing called radar. Radar is a phenomenal technology that bounces electromagnetic waves off of objects to know their speed, size, shape, momentum, distance, etc. And we can bounce them off of the moon using very high frequency radio waves. So you can build a radio tower in your backyard or just rent one and bounce radio waves off of the moon to test how far away the moon is. It takes about 5 seconds for you to send a signal for it to bounce off the moon and for it to come back at any point in time during the day, which means the moon is about 250,000 miles away, given the speed of light and the speed of the radio waves. And it's at that distance the entire day, beginning of the day, late at night, anywhere on Earth. You can do this when the moon like is off in the distance, when you lose sight of it. If you have some friend who starts to seize it from a different part of the planet, they can measure it. It's still the same distance. And this is a problem because if the moon is the same distance within like 10 to 13% for everyone who measures it at any point of time on the Earth, then it can't be going around in a disc shape above a flat surface. Because if it was going around in a disc shape, then you get this strange problem where the moon is here, it's closer to this side than it is to this side. If it moves, it changes to be further away, which means it can't be measured to be the same distance at all times during the day if it's doing this around the Earth. It's just not possible. Which means it has to be doing this big archy thingy. And it can't be doing like little bumps because then somebody would measure it being closer. So it has to be one big bump over the entire planet, anywhere you are, without exception, which means, well, the world has to be round. Because if it wasn't round, then it couldn't be measured to be the same distance at all points while moving. And if the world's round and the moon is 250,000 miles away, and we know that the atmosphere gets less and less dense as we go up, that's a lot farther than when we're going to keep having the atmosphere. So we know space is there. We know it's in space. We know the world is round. We know the moon is real. And we can prove lots of other things, but that is sufficient to demonstrate that, in fact, yeah, space is definitely real. And there's no way around it. I'll conclude there.
You got it. Thanks very much. And with that, we'll kick it into open discussion. Want to let you know, folks, our guests are linked in the description. That's not only here on YouTube. That's also at the Modern Day Debate podcast, which, by the way, we put out our podcast of every live debate within 24 hours of the debate. And you can also find Tom's and Flat Earth Aussie's links in the description box for the podcast episode as well. Thanks so much, gentlemen. The floor is all yours for open conversation.
Well, I wouldn't mind addressing that extremely lame bit of evidence, really, because we don't deny the existence of the moon for one single moment, and so that doesn't for 1 second prove space at all. And I could probably go into some depths about the way the laws of density and buoyancy work, and the fact that with radio waves and radar itself, these things are all calibrated on more or less at sea level, maybe up to mountaintop level, which, we don't go more than maybe 10,000 feet or something with most radar, or, to planes and that. We might pick them up at 40,000, 60,000 feet maximum maybe. And but what we do know is that with density, like we've all done as a kid, stuck our head under the water in the bathtub and noticed how sound is so much louder underwater. And that proves that waves propagating will propagate more and more extremely in the more dense medium. And so as we go into a lighter and lighter medium, what would happen is that those radio waves, this is purely hypothetical on my behalf, but I've thought it through quite a bit, is that they're actually going much, much slower. So they're giving the illusion of traveling a much further distance because they're calibrated in a more dense medium. And so what you're supposing is 250,000 miles might actually be only about 70 miles for all we know, because of how much you've explained the density gradient. Just by climbing a high mountain, we can barely breathe. We can't breathe in 30,000 feet on an aeroplane. If it suddenly lost pressure, we need to put the oxygen mask on. So we could say that that's purely down to density. And we could probably argue back and forth on that. I'm not a radar expert by any means, but I will guarantee you that nearly all radio and radar sort of technology is done more or less at sea level.
Aussie, electromagnetic waves aren't like sound waves. Sound waves travel through the medium. Electromagnetic waves, they just pass through it. They're not like propagating through the matter like sound waves. So electromagnetic waves are like microwaves or
the radio's constantly been called airwaves. You're live on air. That's what has been called. So why would that suddenly change just because you assume space exists?
What they're called airwaves because they pass through the air. They're not because they're like literally passing through molecules of air. They're just
air isn't
in the air. No.
So they're called
airwaves because when place that we use them is above our heads. This doesn't actually pass through the air molecules. It's not using air molecules. That's not how, like, microwaves don't use air molecules to heat things up. It's not how they work.
Okay, well, as I say, I'm no expert in that field. So.
We can build vacuum chambers and use radio waves in the vacuum chambers to know the difference in the speed between the radio waves in vacuum chambers and in air. It's pretty much nothing. There's like no difference in speed. It's about the same speed.
Would that speed be detectable though in such a tiny medium of a vacuum chamber?
Yes.
Because those vacuum chambers are tiny in comparison to the vacuum of space, which is
we can measure the speed of light. Yes.
Okay. Well, speed of light now too. Okay. Cool.
Well, that's the speed at which radio waves and microwaves travel. Is at the speed of light. It's an electromagnetic wave, like light. It travels at the speed of light.
Fair enough. Okay. So the first thing you brought up actually was the vacuum chamber, which I think is actually one of the most interesting parts of credibility or to disprove the existence of space. And it's actually one that I heard years ago from a famous flat earther most people have heard of called Mark Sargent. And I think it's actually a brilliant example of how a vacuum chamber might work. Say, for example, you've got a 2-story house, a full 2-story building that was completely sealed into a single vacuum chamber, and you could create a seal across between the 2 floors. Now, you evacuate the air from both floors, so it's a complete thing is a vacuum, and then you let the air in down on the first floor. And so now that first floor is normal air pressure. Now, if you then release the valve between the 2 floors, what's going to happen? The air will immediately rush up to fill that void, because that's what air would naturally do. It naturally fills the nearest void. It doesn't go towards the more dense place. You claimed it goes towards the bottom of the chamber, and yet experience tells us that we would know that it would automatically fill the top of the chamber given the opportunity to. So you just extend that to the open air, no seals whatsoever around the Earth, spinning through a vacuum of space. The first thing all our atmosphere would do would be to dissipate into the void, whether it sucks or not.
So if we create a vacuum chamber, the biggest one is several stories. It's like 4 stories or something, and we put gas into it. Like we can measure the gas or the water or whatever you want to put into it. It goes towards the bottom. It doesn't fill the chamber. It just goes towards the bottom. Why does it do that?
Well, that's natural laws of density. The more dense thing will always displace the less dense thing until finding a place of most resistance, and the floor is the place of most resistance.
Okay, so
that's a natural law.
So suppose that we this law of density thing you're talking about. If we put gas into a vacuum chamber, the gas should expand to just fill the gas. Like if there's just a single particle, imagine a single particle of gas. Why is it going down in a vacuum?
Well, I'm assuming that the vacuum pump is like turned off at this point, and so it's just like floating. Yeah, well, it's for the same reason that the feather falls at the same rate as the bowling ball, because there's zero resistance anywhere else. And so the path of least resistance to the place of most resistance is the bottom. That's just the laws of density has a natural up and down.
Resistance to what force? Because there's got to be something pushing it down, right? Because it can't just...
No. It's just its mass alone is basically, for want of a better word, it is the force. But really the force is resistance. And because a vacuum chamber is the total lack of any resistance, anything will drop at the same rate in a vacuum.
Why does its mass go down and not up? Like if we flip the container upside down, why doesn't the particle flow to the top?
Because that's just the law of density and buoyancy means resistance has always come from the bottom. That's why the ground is beneath our feet and the sky is above our heads. That's the laws of density and buoyancy. The very first law in science is to make the observation, then make the hypothesis to fit it, not make the observation and then try and make up something that doesn't fit it. It's just what it does.
So there's some force that affects everything, even if it's in a vacuum. How does it affect things in a vacuum? Like, is it like something that like propagates through the space in the vacuum? Is it goes through the space?
And as I've said, it's just the only force is resistance. The vacuum has removed the resistance. So it's naturally just going to go down to the place of most resistance, the floor.
If there's no forces, then it won't go anywhere. So if it's going down, there has to be a force causing it to go down. So
Well,
no
it's called the
forces
properties of
mean
matter.
no movement.
It's called the properties of matter, and gas being a fluid, it will still flow to fill its container. So if there's just a single molecule, well, it's not really going to fill its container very much, is it?
Yeah, but
enough
why is it going to move
gas,
anywhere?
It will fill the whole container equally, but it's just the properties of matter. We don't have to make up anything new to describe what matter does. We make the observation. The more dense thing always goes down to a place of most resistance. And if it's a fluid, it'll keep on flowing until finding a container that can hold it, which is what we call sea level.
So yeah. So I'm asking here is why does it go? What causes it to go down? If there's no forces, if it's just density and nothing is pushing on the molecule, then it can't go up and it can't go down. It can't move at all. So if it's just in space, if there's a single molecule in a vacuum and it's just density is the only force affecting it, then it will not move. The only way density could cause something to move is if something that is more dense is above it or less dense is below it, because density is a kind of friction. So if there's no object above it and no object below it, then density, relative density, can't actually cause it to move. There has to be something else there to actually touch it to make it move for density to cause it to move.
That's not necessarily the case. Like, as we know, that object at rest remains at rest unless acted upon by another force. And generally speaking, what that force will always be is lifting it up in the first place. Like you've added a force by adding that molecule of gas to the vacuum in the first place. If you didn't add it, then of course it's not going to go anywhere. You've added the force, and the molecule is just reacting to that force.
Yeah,
you know, it's the reaction. It's not a force in itself. It's the reaction to being put there somewhere where it didn't have enough resistance to support it.
Again, so we put the molecule in. We didn't put the molecule in at the bottom. We put the molecule in like in the middle. So we want to know, why does the molecule go down and not up? If there's relative density, the laws of density all say that you have to have one object of a greater or lesser density to push a different object of a greater or lesser density. In a vacuum, there's no object. There's the only molecule. So there's nothing to push it up, nothing to push it down. Why does it go down?
Because the vacuum won't resist it. I think I've already explained that several times now. Like, do you have any other questions?
So gravity. So because gravity is pulling it down, like there has to be something pulling it down.
Because there's no resistance. You don't float in air.
Resistance means stopping. Resistance is like something trying to stop it from falling.
Exactly, and that's what the floor does. The floor is dense enough to resist it, so it stops at the floor. That's where it comes to rest.
If there's no positive force causing it to move, then it doesn't matter if there's resistance or not. So if there's nothing causing it to come down, then it doesn't need any resistance. It will just stay there. So there has to be some force causing it to go down for the floor to resist against. So there's a force causing it to fall. It has to hit the ground, and then the resistance stops it from continuing to fall.
That force, we got a word for it. It's called putting. The scientist put it there.
Putting?
Yeah, he put it there. If he didn't put it, he didn't lift it or somehow inject it into the vacuum state. Like if you kept the vacuum pumps going and you add that gas molecule into it, it would get evacuated as well, because that's what the pumps do to create the vacuum state. So somebody has used energy to put that molecule of gas in there, which is the equivalent of lifting, throwing, kicking, shooting, whatever, and put it in some way or another. And that is the action. And the falling to the ground, the place of resistance, is the reaction. That's all it is. Just action, reaction.
Well, we can put something at the top of a container. We can throw it up. It still comes down every time. So no matter where we put it in the box, it's still going to fall down because of some force that's actually going through the container that has nothing to do with density.
Yeah, it is that due to density. It's resistance. Buoyancy is literally resistance, and so the floor
it can't be density because density only applies between objects. So there has to be an object of density 1, an object of density 2, and they have to hit each other for density to transfer a force. If you're in a vacuum, there's no two objects. It's just a vacuum.
There is. There's the gas molecule and there's the floor.
Yes, but remember, we're saying the gas molecule is in the middle, so it's not touching the floor, right?
Not until you release it. Once you've released it, there's nothing to resist it from going to the floor except the floor itself.
That's the part I'm asking about. So once you release the molecule, now there's nothing above it, there's nothing below it. There's no molecules of any density above it or below it to push it anywhere. So density can't cause it to move, but it's still falling for some reason. So it can't be density, but it's falling for some reason other than density.
Well, because it's more dense than the vacuumous state. The vacuumous state is lack of density altogether, which therefore means lack of resistance altogether, which means everything would fall in a vacuum. So that's why outer space is so impossible, because everything that we see in space would fall, because that is just the universal thing for things of density to go down. That's why we see meteors. If we see them, they always go down. They're always going to the place of the most resistance. The whole idea of space is ridiculous. Like I said with the Thor's hammer example, you know that if you threw it really, really hard, it's still going to come crashing down to the ground eventually. It's not going to keep orbiting, just missing the Earth again and again and again, like we say the moon does. So to say that the moon orbits us due to gravity is the most ridiculous thing ever. It is the equivalent of the gas molecule sitting in the middle of the chamber with no reason to fall any direction whatsoever. It shouldn't just miss the Earth every time in free fall. It should just miss us once and keep on going, and we'd never see it again. The very idea that you're trying to bring up contradicts itself when we then apply it to the things that we do see in reality. You mentioned the moon going around in a disk. Well, that's the way we see all the celestials move. We see them all move due to some sort of electromagnetic force at a pretty much an equal distance away from Polaris, the center fixed point of everything. The sun being the point of the equator, which happens to also be the place where Polaris disappears from view as you move with distance away from it. So everything's measured in circles around Polaris, the fixed northern center of the fixed planar Earth we live upon, and the moon being a physical object. I won't say that the light of the moon that we see is actually the physical object. I do believe that's a projection, but that's going into something outside of the realms of the discussion of space. But it moves due to electromagnetic force of some sort that we don't exactly know, but it also drives the tides around ahead of it, which can be explained by the resistance force, the same force that should hold it aloft above the Earth, is what then has a pressure gradient onto our saltwater oceans and drives the tides around. In the heliocentric model, you've got one thing that says tides is caused by the moon, and it's its gravitational pull, which you can't pull water for a start. You can repel water very easily. You get a straw above a glass of water and blow through it, you can watch the water repel very simply, but no matter how much you suck, if the straw above the water, you won't move it an inch. So it's very easy to repel water. So with the moon going around the stationary planar Earth every 25 hours approximately, that aligns perfectly with our tides. The ocean hits one coastline and then the rebound sends back the secondary high tide on the opposite coast. The global model using gravity, first of all, the moon is absolutely impossible because the speed of the Earth going around the sun, 1.6 million miles a day, and the moon's only in free fall, some 2,800 or 2,280 miles per hour around the Earth, backwards of course. There's no way that it could even keep up at those speeds that it's attributed for the Earth to be going around the sun at its ridiculous 500,000 miles an hour plus speeds. And yet the moon is meant to be pulling 2 tides per day with only one mass. You get one massive high tide only and one massive low tide every 25 hours. And that just completely disproves the heliocentric model in itself. Just the moon alone disproves it. The gravity of everything disproves it.
Have you ever hit a glass of water? Like if you hit or put your finger in, you notice there's multiple waves that happen, and when the waves hit the edge, they bounce back and create waves going the other direction.
Yeah, like in a tub, if you sit up, suddenly the water hits the other end and then comes back and spills over behind you type of thing. The splashback effect is quite often greater than the initial force that pushed it in the first place, and that's what creates the secondary high tide. Yeah,
so the moon could definitely create tides going in both directions, couldn't it? Because if it creates a big, like if it pulls the water in one direction and the water is then going in that direction, well, then the water on the other side of the planet is going to move to fill the hole, right? Like if you stand up in a bathtub, the water that you have displaced is going to be filled by the water behind you. Well, even though there's a wave going in front of you, there's another wave coming behind you to fill the hole, right?
Yeah, but also we've got the same argument, only I'm saying that the moon repels the the tides because I've actually spent years and years of experience on beaches and watching the moon, watching the tides.
The moon repels the tides?
The
What?
weather and everything.
The moon repels the you mean like so the moon pushes the water?
Yeah, you
away?
watch the moon approaching from the east, because I live on the east coast here, and you watch the water creeping up across the dry sand. Like when water creeps across dry sand, it behaves completely differently from how it does on wet sand, where it sinks in quite rapidly. The dry sand sort of has a bit of a crust on it, and so it sort of has a quicksilver type of effect. So when you're sitting there on your tower watching the ocean and you see little bits of sticks and flotsam and jetsam floating up, crawling across like on a bubble almost across the dry sand, it's quite a unique sort of experience, which you get to see with years of experience sitting on the beach watching tides and so forth. And you think to yourself, well, how's that happening? If the moon's over in front of me, approaching towards me, why is the tide coming ahead of the moon? And I couldn't work it out at the time because I was still a bona fide globe believer at the time. But now it makes perfect sense, is that the moon is actually repelling the water ahead of it, pushing it. And then as it reaches the coast and goes overhead, then it sort of is also slightly pushing it away with that splashback as it keeps on going across the other side of Australia and right around on its daily circuit of about 24 hours, 50 minutes. And our tides every day are about that extra 50 minutes later every day. So
have you ever
the tides, I don't believe it pulls them.
so have you ever like put your hand in water and just pushed it like this? Do you see what happens when you do this?
Yeah.
It's like there's a big pile of wave here and a big hole here of no wave, right?
And you'll also get vortices spiraling away either side
Yep.
in opposite directions, disproving the Coriolis effect. The Coriolis effect is just a reaction of the sun itself as it goes around the equator every day. It creates heat waves, basically, from the light and everything that creates low pressure systems. And that's why storms, tropical storms, will rotate either side of the equator.
So the question was, if the moon was pushing the water like your hand pushes the water, then there's going to be a big blob of water in front of the moon and a big hole of water behind the moon. But we don't see that. We see an equal distribution of a big blob in front and behind, which means
you're
it's not pushing.
what I said. You're misinterpreting how I suggesting the moon repels it. I'm saying it repels with a downward force, which would create a spot directly beneath it. But it's not a huge one. It's only a very, very light force, a bit like how gravity is such a weak force. I call it a diamagnetic repellent force, a bit like when you've got two pole magnets, the two similar poles trying to push together, they repel. And I believe that's the force that holds the moon above us. And that's a weak force, but it's sufficient because the oceans are so massive that it will push around 1 or 2 meters, which is really, in the overall scheme of things, very, very tiny. It's not a massive wave like you're pushing with your hand. It's a repellent downward force pushing the waters, generally speaking, in a broad way ahead of it.
So the moon pushes the water down. So if we're under the moon, then the water level should be lower than any other point of the day, right?
Yeah, technically, that would be the lowest point.
But it's not. It's the highest point.
Is it, though?
Yes.
And how much experience have you spent at the ocean watching this?
Watching it? Like, I've seen tides come in and tides come out. We do know how that happens, Bill O'Reilly.
Yeah, well, so have I. I've spent like 30 odd years plus watching tides, surfing in tides. Like when you're a surfer, the tides are really important, especially on point breaks, because, certain rocks appear at a lower tide, and it's a lot safer on a higher tide. When you're at the open beaches, the sandbars get a lot shallower at a low tide. The waves might get a lot fuller at a high tide. There's not as much fun. So there's a lot to do with surfing over all the years where I've learned to observe the tides and so forth. And because I've also spent all this time with a moon chart on my wall, which is how I know that tonight's full moon will be at exactly 3 minutes past 10 p.m. here in Australia, in our Eastern Standard Time. I know the moon phases particularly well, and I always make a point, especially when I lived at the easternmost point of the Australian mainland, the famous Byron Bay. I would always go on the full moon night to watch the full moon coming up, because it always coincides with the sun setting, which is like above the flat earth, the yin-yang symbol as we would see it if we could look at it from above. So I know the moon and the tides rather intimately through many, many years of experience. And I can tell you that as the moon's approaching, you get the high tide, but by the time it's overhead, the tides are actually rapidly running back out again.
maybe you just not looking when it's overhead in the right direction. Like this is like when the
I'm
moon's
very
overhead
aware.
during the new and the full moon, the tide is the highest when it's directly above you. When it's directly above you. Like
No, I
maybe
don't think
you're
so
looking
actually,
in the
because
wrong. Oh, maybe because
I'm
you're in Australia, so it's technically to the side of you.
what I've noticed is that when we get our king tides on the full moon, which are right at the equinoxes, so in the next month's full moon, that's when we get the most king tides, and they always happen as the moon is rising. So that's when the moon is on the eastern horizon from our perspective. It's not necessarily rising; it's always the exact same height above the Earth, of course. It might vary slightly throughout, your super moons and so on, but it's more or less the same height above the Earth at all times. And so it's going to have the most repellent force when it's at the horizon coming into view. And then as it passes overhead, it's starting to repel it back again. And I think you'll find that the high tide is highest around sunset or soon thereafter. It doesn't happen at midnight, which is when the full moon would be directly overhead at midnight, and it's setting as the sun is coming into view again. That's how
Why
the moon
would it be
phases
directly
work.
overhead at midnight? That doesn't make any sense.
That's how the phases work. The full moon, the moon itself only shows all night, one night of the month. And that's the night of the full moon. That's
doesn't mean it's
night
overhead.
So
like that doesn't mean it's directly overhead. Like the moon is only in front of one part of the Earth at a time. Even on the flat Earth model, the moon is only above one part of the Earth at a time, and then it moves to it being above a different part of the Earth. It's not like it's on midnight, it's directly above every single part of the Earth everywhere. That's not how it works. So obviously, take your model of the flat Earth model. So the moon goes around like this. The moon goes around like this, right? Like on the flat Earth, like this is your model, something like this.
Something like that, yep.
So it's only around this very small, like directly beneath it, only covers like one like 10% of the Earth with the Gamefly disc. It's only going to be the moon is only going to be directly above about 10% of the Earth. It never goes above here, never goes above here, never goes above here. It's only this exact circle thingy that it goes directly above, right?
Okay, well, that's a huge misunderstanding on your behalf of how perspective works. The higher something is, the more you can see. And so at the height of the moon, half the world at any given time is capable of seeing it. At one point where it's rising, it'll be setting at the other point, and then that 50% in between that is going to see the moon. And so on the full moon night, because we do have time zones, the sun and moon are moving synchronously with one another. So because the sun sets at the time the full moon rises, as it goes around, the sun, which is over wherever it's overhead, is their local midday. So we've got 24 different time zones around the planar Earth. And so the moon on the full moon night, in the middle of the night, will be directly overhead wherever you look at it from, because each time zone is separate. As I say, there's 24 of them, loosely speaking. Like some countries divide them up a little bit differently, but there's loosely speaking 24 time zones, and the sun is like the hour hand of the 24-hour clock. And half the world can see the sun or the moon at any given point for at least, on average, 12 hours of each day.
Right. So my question is if the moon is here, it's like on this little globy thingy, that means that the water directly beneath it is going to be affected more than the water like 10 miles to the left or 10 miles to the right, correct?
It's not noticeable enough. It's a very broadly spread out push. It's not a very strong repulsion, as I said. It's only pushing the entire trillions and trillions of litres around about 2 meters at the coastlines. And the coastlines obviously have a greater effect because of the shallow water. If you know anything about waves whatsoever, they increase in speed and they gain in height when they get closer to the coast. So tides in the actual open ocean are probably negligible. You wouldn't even notice them at all. It's only on the coastlines where you do actually notice them, because you notice the water receding and lowering compared to the actual coastline. And a 2 meter difference, it might seem significant for you when you're trying to go fishing or surfing or whatever, or boating in a shallow water that opens into the ocean. But generally speaking, the tides are pretty well insignificant on the size and scale of the planet Earth.
So you're saying the moon pushes the water, and in your model, the moon is a lot closer than in my model. So if the moon pushes the water it's going to push it closer to it a lot more than farther away, right? Or does it spread out the force evenly no matter how far away the water is?
Well, as I said, it's a very broad sort of thing. It's pushing the entire ocean around from a central point, but it is very far away still. Like we tend to think of, in terms of hundreds of thousands of miles, which is what you guys attribute the moon to being, whereas I say the firmament is no more than 70 miles high, and the moon is an artificial satellite made here on Earth of an unknown size, but it's this side of this firmament. And I would say it's probably far less than the 70 miles high. And I say that the radiant energy that it picks up off the sun gets projected into a much lower place again, which I call firmament B, which I would say is only 12 to 14 miles high. That's our blue sky limit, where if a pilot goes really high up and he goes out of the blue into the black, that's what I call the firmament B. That's the noble gases that give us daylight level. And so you can still be in the blackness of space, as they call it, but it's still well within Earth's atmosphere. It's just it's above the layer of gases which give us daylight, which is completely different from sunlight, which casts a harsh shadow. Daylight basically can light up an entire room without being able to see the sun whatsoever and cast a very blurry shadow. And then, of course, you've got twilight, which is the very edges of sunlight. Well, the moon, I believe, takes this light from the sun and projects it into that particular layer of the gases to create a plasma apparition of itself. So even the moon that we're looking at isn't really the moon itself. That's why so many people think of it as plasma and not a solid thing. But I say it's still a solid thing, much higher up and much smaller than it appears. I mean, have you ever played shadow puppets, for example? As a kid, you get a torch and you make shadows with your fingers and you make these animals on the wall. Well, if the moon casts a 70-mile shadow on Earth, it's quite possible it's only 7 miles wide, up so much higher, but when it passes the sun to eclipse it, it casts a 70-mile shadow, a bit like a shadow puppet. Okay. So it could be much smaller and much nearer than what we actually believe.
Well, it can't be, because we can literally bounce radar off it. So does radar work? Does radar work?
Well, as I say, I don't believe it works the same as what it does through the density of air. I believe it works differently. We have to agree to disagree with that one.
No. Does like radar here on Earth, like when we bounce it off of a building or a plane in the atmosphere, does it work?
Of course it does, in the medium of air. That's what it's calibrated for. That's
so
how
if the
know.
moon was
we
in the atmosphere,
tiny layer of what we exist in.
So if the moon was in the atmosphere, in the air, we could bounce radar waves off of it.
Yeah, but there's no air up there. We know that. We know for a fact that the air has this gradient layer.
So space is real? You're admitting space is real?
I'm not admitting space is real. I'm admitting there is space between things and there is a void between us and the firmament, but I don't believe we can go above or beyond the firmament. Never have, never will.
So there is a place where there is no air, and that's space. There's just below the firmament. There's spaces real below the firmament.
A helium balloon, we can send them up with cameras, and to the best of my knowledge, the highest we've ever gone is about 130,000 feet, which in terms of miles, it's about 23 to 24 miles. It's not particularly far, but as far as that's concerned, when it comes to height, it's extremely far. And one thing you will notice once they get to that height, you do not see the moon at all. You cannot detect it. You do not see stars at all. You see a sun, which seems to be about twice the height of what we see, that blue fuzzy layer of light below. So that's why I sort of assume that the sun itself isn't the sun either. It's actually a hotspot apparition in the firmament, which gives it the visible light to us. And so that tells us the height of the firmament, not actually the sun. The sun varies in different heights above that firmament, which is what gives us the seasons in this model.
So there's a few things I wanted to bring up. First is that if the moon was directly above a place and moving around in the disk shape, then the highest tide would be in front of the moon, not behind it. So your model seems to disprove your own evidence that you have presented. Also, it's the highest tide when the moon is above us.
Quite slowly. They take about 6 hours and 12 and a half minutes on average between each tide, from high to low to high to low again, which averages out at 24 hours, 50 minutes. So it's not as though it's pushing very directly in one particular spot. It's a very generally, broadly spread out, slow ebb and flow of the tides that's caused
Yeah,
by
the
the moon.
moon is
Those
6
colours
hours
have to be
ahead of where it
water.
would need to be to push the water down. So if the moon was pushing the water down, it would have to be 6 hours like to the left of where it is.
It's just pushing it ahead of it, yeah.
That for it to do that, it would have to be 6 hours off where it currently is. So the spacing of the moon is incorrect for your model. It would have to be halfway
No,
off.
I say there's a delayed reaction. It's within that 6 hour period.
Delayed reaction.
Yeah, because it's a lot of water to move around. So by the time it reaches the highest point, by that stage, that's when the moon's starting to pass it, because it's pushing a huge amount of area. I mean, you're talking about a disk of some 25,000 miles as far as we know the equator is. Now, I'm not saying that the moon follows the equator the way the sun does. I'm thinking the moon is on a bit more of an elliptical path, which is why it changes signs of the zodiac so rapidly. It goes through them every 2.5 days or so, whereas the sun takes an entire month to change from one house to another. So the moon is sort of a lot more elliptical. So it's not as concrete as what we would say if it was the sun causing tides, and we would know we'd get the exact same tide at the exact same time every single day throughout the year. But because it's the moon is an anomaly in every sense of the word, both on the heliocentric model and in reality. And so the tides broadly.
So how does the moon push on the Earth with a delayed force? Like, is it blowing on it or something? Like, how does the moon, using relative density, push on something that since it's lower, it must be of less density than the moon, and do it delayed?
No, you've misunderstood what I'm saying is the force. If it's relative density, that's what would hold it aloft. If it was, say, filled with helium, for example, which we don't know one way or another. A lot of people have proposed that it is filled with helium-3, and it's a very valuable thing to go mining someday in the future, but that's neither here nor there. It's what I call the diamagnetic force that holds it aloft, the repellent force, like magnets. So like if the Earth is negative and the moon is negative, then that force is what's holding the moon aloft. And because the oceans are full of electrolytes, which is what dissolved salts are in water, that's basically a natural force that holds it aloft and reacts to that force which keeps it aloft in the first place. It's just a reaction. It's not density and buoyancy when it comes to driving the tides. Diamagnetism.
So the moon is being held up by a magnetic pole, and caused by electrolytes in the water. Is that correct?
Repulsive force. I'm saying the electrolytes react to that force. I'm not saying it's caused by them, but they are what react. That's why massive freshwater lakes don't react to the moon hardly ever. They have some dissolved salts in it, but not very much. That's why they're fresh. But the higher the salt level, the more it reacts to that force, what holds it aloft.
So is this the same as a magnetic field, or is it just a different thing? Just you're just using magnetic field as like an analogy?
No, diamagnetism. It's repulsive.
But it's actually a magnetic field, so it would affect
like,
compasses.
Have you ever played with bar magnets, right? And you put one on the table, and then you get the other one, and you rest it here, and it sort of just floats there if you get it balanced perfectly right.
Yes.
Well, that force that's keeping this one anti-gravity balanced, that's a similar force on a much larger scale as to what I believe holds the moon aloft. And the other electromagnetic force that keeps everything going around Polaris, it's somehow joined up into that same cosmic soup, for want of a better word, that keeps everything moving more or less as one around Polaris. However, the moon, being physical, has some slight amount of drag as opposed to the lights in the ether above the firmament, where everything moves as a single body apart from the wandering stars.
Okay, so there is a magnetic force holding up the moon, but we can't detect it. Like for magnetic forces, we can hold a compass up and the compass will point towards the poles, but it doesn't point towards the moon ever. Why don't magnets point towards the moon if it's being held up by this magnetic pole?
Because, as I said, it's diamagnetic, repulsive force, not attractive force. The North Pole, Polaris, is the magnetic force, and that's what all compasses point towards. That's where north always is, and south is always away from that. It's not pointing towards any other pole. It's just simply pointing away, because a straight needle, for want of a better word, has to point two directions. One of them towards the inner center, like spokes on a wagon wheel. South is always outwards, hence the word southwards, and north, inner, goes towards the inner North Pole. And the equator just happens to be the place that the sun goes around. It just happens to get higher and lower, which is what gives us the seasons. And when it's at the midpoint between the two, that's where we have our equinox.
If north is the pole, then south is away from the pole, and the moon is like to the right and left of the pole. So it's like 45 degrees off. So how is it being held up?
Up to the right and left now.
Right, or the moon isn't like directly above the North Pole, right? It's going like in the middle of the Earth somewhere.
That's right. Yeah. Yeah. So the diamagnetic force repels it from the Earth and from the magnetic center, which keeps it more or less locked at that distance away from the pole.
Right. So there should be somewhere where we can hold a magnet where the north is pointing the opposite direction of the moon, right? And the south will point towards the moon, because for it to hold the moon up, it has to like push upwards, right?
No, the moon has got nothing to do with how compasses work. Nothing to do.
But you just said the moon is being held up by this diamagnetic force, right?
Yeah. Diamagnetic, not magnetic. It's the opposite of magnetic.
So if it's the opposite of magnetic, then the south should be pointing towards it, correct? The north should be pointing away from it.
Look, if you get two magnets, if you hold north and south together that way, or you hold south and north together this way, they're both going to bang together.
Right.
Whether you have north or
anywhere
south,
in that. So you take those two magnets, you can hold a compass in between those two magnets, and it'll point at both the magnets. You can tell you where they are, what direction they're pointing, which one's the positive and negative. You can take a compass in between any diamagnetic relationship, and you can map out the entire field.
Do you know what diamagnetic actually means?
Becoming magnetized in 180 degree something field.
No. It's the opposite of magnetism. It's like if you get a whole bunch of tiny ball magnets together and you stick them in and make a big ball out of them, you can get another magnet, a bar magnet, and hold the north pole to it and it will stick. And then if you turn it around and put the south pole to it, it will stick as well. So it's sort of like non-magnetic. So whatever this force is, I know that sounds counterintuitive to what I've been saying about how it's a repulsive force, but diamagnetism is not the same as magnetism. Now, I don't know. I'm not the genius who designed the moon and made it work. I don't know exactly how it works. All I'm saying is that it's a repulsive force, and that force drives the tides around. But a diamagnetic force is not what you're trying to say it is as magnets. If you put two magnets near a compass, the compass will just get stuck in the middle and it'll average out. It will always point towards the strongest force. And on Earth, without any other metallic or magnetic influences, the magnetic compass always points towards north, irrespective of where the moon is. The moon's got nothing to do with it.
If it's a repulsive force, then you should be able to measure it with a compass. If it is an attractive force, you should be able to measure it with a compass. If it is using the force of magnetism in any direction that isn't completely still, you will be able to measure it with a compass. So if the moon...
I disagree. I don't think it could be measured. We need an extremely sensitive instrument to measure what I call, because diamagnetism is a very weak force. You'd need something extremely, extremely sensitive, probably more sensitive than a seismograph or whatever you use to measure earthquakes, which, by the way, is the only motion we've ever detected here on the planet Earth, despite the heliocentric model claiming it's whizzing and twirling at millions of miles an hour through space. And no motion has ever been detected apart from earthquakes. So
it's powerful enough to hold up the moon and to create the tides, but we can't measure it with a compass.
Not with a compass, no. A compass is a very weak magnet. It's pointing towards the North Pole, a very strong magnetic force. The North Pole seems to be the driving force of everything.
If this force is causing the tides to move billions of pounds of water and we can't measure it, you don't see a problem with that.
I'm not sure if anybody's even tried to measure it, but I would suggest that using a compass is the very last thing you would use to measure a diamagnetic repulsive force as weak as what the moon gives. I mean, it doesn't affect the land, it doesn't affect fresh water, it only affects salt water, very large bodies of it. And so basically, I think the test for measuring it is the tides themselves. That's what proves it. We don't need to test anything more than that because we can see the results from the tides that match perfectly with the cycles of the moon.
So by diamagnetic, like how do you spell that? Is this the same as the science, the DIA?
Like magnetic with DIA before it.
Yeah, so that just means repulsive magnetic fields, which is the exact same. It's not the opposite. That would definitely be 100% verifiable through a compass.
Well, I've never detected it. It'd be interesting to detect. Maybe that's something.
In science, diamagnetic and paramagnetic are opposites. They're the direction of the magnetic field. The magnetic field is still there. It's still measurable.
Okay, well, fine. But all the same, this is hardly really debating the topic of the existence of space. Like, you know, you've used the moon as an example to prove space exists.
Yep.
I use the moon to prove space is impossible. It's the same argument. If, say, you're on a bicycle, you're riding down the street, and a fly starts buzzing around you. Now, if this fly stays just out of arm's reach the whole time, or just the same distance from your head, that means that as you're going down the road, as the fly comes in front of you, it has to fall down around behind you and slow right down, accelerate back around you and accelerate back in front of you, slow down, accelerate, slow down the whole time if it's to remain the same distance from you. Now, that requires energy, a force. What force does the moon have to keep speeding up, to race ahead around us every 27.3 days, going backwards nonetheless from west to east, as the Earth moves 1.6 million miles every day over this 27.3 day period? It's gone millions and millions of miles to go 1 month around the sun. What force is the moon using in free fall to stay a constant distance from the Earth?
Gravity, centrifugal force. It's being pulled.
No, but I discussed the Hemisphero event. As soon as you let go the tether, the thing goes flying off in a straight line. So if you're saying centripetal or centrifugal force, that can't be the case at all. It would have to just miss the Earth once and continue in a straight line unless another force acts on it. What
Gravity.
Force is that? You can't say gravity because gravity would pull it to Earth.
It is.
It would pull it to Earth.
So it's like gravity is like here. So if you pull this way, gravity is going to pull it towards us. And it's going to, like you see, it's going to do this.
Yeah.
If the rate of gravity is the same as the rate of the objects are moving, then it'll stay the same distance the whole way away. So if you imagine like two objects falling at the same time, essentially, the moon and the Earth are falling, and they're the same distance away. But now, if you add like a little spin to it, it'll go around in a circle, going in orbit.
Right, but so this is your Earth, right, and it's going this way, and the moon's going around the Earth. So when the moon is in front of the Earth, going this way around the sun, how can gravity repel it from the Earth? Gravity would make the Earth crash into it. It's repelling it, keeping it the same distance away the whole time. Because you're saying gravity's pulling the moon towards us. Fair enough, when it's behind us, gravity might pull it that slight little bit, even though we're going 67,000 miles an hour through space. You're still pulling this moon away from 250,000 miles. But when it's in front of us, of our orbit of the sun, during that half of the month, or that few days anyway, when it's exactly in front, it'd have to be repelled. It'd have to be going faster than the Earth.
Yeah,
the Earth would trap into it.
Have you ever like held a rubber band?
I've held a rubber band. Yeah.
So if you take a weight or a ball, like a tennis ball, and you tie it to a big rubber band, and you spin it around your head, the rubber band is going to be pulling it toward you the entire time, right?
Yeah, that's correct.
But the force of you throwing it is going to be pushing it away from you the whole time.
Yeah, that's also correct.
So if those forces are about the same, then the ball will start to balance in a big circle around you, won't it?
Absolutely.
So if the moon had been launched at some speed, and gravity is like the rubber band, and if that speed the moon was going at was enough to counterbalance the pull of gravity, then they'll start to get into a locking thing, just like the tennis ball and the rubber band, right?
Well, there you go. There you go. You've just disproven how it could possibly work, because the vacuum of space can in no way be equivalent of a rubber band, which is a forceful tether, as I said, with the tether. As soon as you let it go,
space
it's
isn't the
gone.
rubber band. Space isn't the rubber band. Gravity is the rubber band.
That's what you said, but all that space in between is a vacuum. So how can gravity be a rubber band? Because the rubber band is constantly trying to pull it towards you.
Remember, so if you're in a vacuum chamber, remember the example I used with the vacuum chamber where the molecules fall even though they're in a vacuum chamber?
Yeah, exactly.
So the force goes through the vacuum just fine. It can travel through the vacuum and grab stuff.
Uh-huh.
So,
but there's nothing tethering the moon, and the Earth's orbital speed is what destroys the existence of the moon, because the moon isn't going fast enough. Like the kid riding the bike, if the fly is staying the same speed, then he'd crash into the fly when the fly was in front of him. And if the fly was behind him, he'd be going too fast if the fly didn't accelerate with force to get back around in front again. He would have to be using a force to accelerate to get back in front. That's the whole problem with the moon. It has no force of acceleration other than this invisible rubber band, 250,000 miles long, which doesn't exist. As soon as you let go of that tether with the hammer throw, the hammer flies off.
Gravity doesn't let go. It continues to pull on it towards the Earth, and the moon continues to be moving in a direction parallel to the Earth with the speed, and gravity continues to pull it, which then creates the exact same thing as the tennis ball on the rubber band. It doesn't ever stop. It doesn't let go. There's no letting go.
But even the tennis ball on a rubber band, you still have to assume that the person holding the rubber band is moving faster, multiple times faster the direction, in one particular direction. Like you might be swinging it around on a tether the whole time, and that's fine if there's a solid tether there to hold it in place. But as you're going in one particular direction, the Earth, 67 or 66,600 miles per hour around the sun to go almost 1 degree per day, which is the equivalent of 1.6 million miles, which no flying vehicle could possibly keep up with, which is another thing that I didn't have enough time to put into my introduction. But assuming we were in outer space and the Earth is traveling that speed, no rocket we ever sent off the Earth would ever have enough speed to catch back up again, let alone a big giant ball of rock called the moon have enough speed to ever catch back up again once we left it behind us. If it's in front of us, we're going to smash into it. There's no two ways about it. That disproves space.
The tennis 100%. Ball. The tennis ball is moving faster than the guy holding the tether.
But it's not.
What?
See, in heliocentricity, the moon is going 2,280 miles per hour to go once around the Earth at its distance every 27.3 days. But every day, the Earth is traveling 1.6 million miles. It's traveling 66,000 miles per hour.
Those add together. The moon is going the Earth speed plus the moon speed. So the moon is traveling faster than the Earth. It's like the tennis ball. If you're holding a tennis ball on a tether in a train, the tennis ball is traveling your speed, the train speed, plus the speed you're spinning it. The moon is traveling the Earth speed plus the speed it's spinning around the Earth. So it's going faster.
Plus then the speed of the sun. Now, I know a little bit about speed. Galaxy, I know about speeding bullets. We cannot see speeding bullets with the naked eye. And yet these things are going like hundreds of times faster than speeding bullets.
We can't see bullets because they're small. If they were bigger, we could see them.
It's going 10 times faster than a bullet.
Yeah. If bullets were bigger, we could see them.
Do you really believe that?
Yes.
At the speeds they're going?
Yes, we've done it. We put the tracer thingy on the bullet so it reflects light so we can see them. We can see the big rockets that they launch with the electromagnetic guns. We can see those. They're big. They can see them. Rockets like missiles travel faster than bullets. We can watch them in the sky.
Well, I find it highly dubious considering the speed that the Earth itself is going at. That then means, though, that these things are going their speed, 10 times bullet speed, plus, another 60 times bullet speed that the Earth itself is moving. It's just all too much. It's the story of the little old lady who swallowed a fly. Once you swallow that first lie, you have to swallow lie after lie after lie to the point it becomes ludicrous. It's equivalent of a little old lady swallowing a horse. the heliocentric model is dead, of course, because it's just too much to fit in to a mind that understands things with common sense, starting with the most simple little thing. To swallow the first lie of being a spinning space ball, then another lie had to be spun around it to swallow the spider with this big web you weave to swallow that spider. Then you need to swallow a bird, which is
how far away do you think? How far away do you think the firmament is? Where the sun? You said that the sun was on the firmament or something, a bright spot on the firmament.
I suggest that the firmament is probably in the vicinity of 60 to 70 miles high. And that is where we see the apparitions of light, such as the sun and stars. That's where they appear to us as visible light.
60 to 70. Okay. And if we're traveling, how fast is the firmament moving?
We're not moving. That's the thing.
Firmament.
Stationary planar Earth, we don't move.
Firmament. How fast is the firmament moving?
It's not moving.
The stars and the sun aren't moving?
They rotate around above us, and as we know, it takes 24 hours for the sun to make a single cycle. The stars do it in about 23 hours and 56 minutes. The sidereal day is the star's motion.
Yeah, so if it's 70 miles above us and it goes across a 360-degree circle around us, how many miles is it across?
See, this is the thing. You're not understanding. When we look at a visual phenomenon through a firmament, we're not actually seeing what we think we're seeing. We're seeing an apparition of light created by the actual thing. We don't know how far away it actually is, how fast it's actually moving. All we know that from our perspective, we see it takes 24 hours to go around what I consider the equatorial circle for the sun, which would make it approximately 1,040 miles per hour. But because it's up so much higher above, it seems to be going much slower through the sky because we're seeing an apparition of it, and we see it in a direct line of sight between us and the source of the sun. So that's why it can appear in many, multiple more places than what would be logical to us, thinking it's just a single point source of light, when in fact, if you think of the story of a fish under a lake, a frozen over lake, when it looks up towards the sun, it sees a hotspot apparition on the ice, and to another fish, even just 50 meters away, it looks up through the ice, it'll see a completely different hotspot apparition in a completely different part of the ice. Okay. But for all intents and purposes for both those fish, that is still the sun. And that is what we have the problem with here on the planar Earth. When we're looking up at an apparition of it, we think it's the sun, but it's not. It's a hotspot apparition created in the firmament, which makes it appear much, much further away than it is because we're using the wrong method of calculating its height.
So when you're on a plane and you're like walking up and down the aisles and you're going 600 miles an hour, like, does that feel any different from walking like on the street going 0 miles?
Actually, it does. Yeah, it feels quite distinctly different.
How? Because you don't notice any difference.
You do. It takes a little bit of getting used to. Once you've got used to it, you don't notice it so much. But it is actually, you do notice something. But fortunately, if you're in an enclosed, pressurized capsule, you may as well, for all intents and purposes,
so going half of the speed of the sun in your model, you can notice almost no difference, like almost barely any difference going 600 miles an hour.
I notice it, definitely.
Barely any difference. You notice barely, like you can still walk just fine. Correct. You can still sit down, like you can still breathe. Going 600 miles an hour, you notice almost no difference.
Because we're in a pressurized, sealed cabin.
Sure. So now let's imagine. Let's imagine if we put the entire planet, or God created a super big train, and he put the entire planet and the firmament on the super big train and decided to make it go 6,000 miles per hour, but just started to accelerate it really, really slowly. Would we notice any difference?
No, you wouldn't. But you wouldn't need to go and invent speeds, though, that didn't exist and couldn't be detected.
So there's no problem with actually going the speed that NASA says we're going at. There's no problem with the speed of the sun in the galaxy, or the moon going around the Earth, or the Earth going around the sun. Those could all be possible, and we wouldn't feel them at all because God could do it with the train.
Well, no, that's completely wrong once again, because when you consider that in the heliocentric dialect, basically you've got the Earth going 66,000 miles per hour around the sun. It's also spinning at 1,040 miles per hour at the equator. So the whole thing, on average, is moving at about Mach 86. But the fastest part of it is on the outside, which would be the night side, the side away from the sun. It's actually going almost Mach 88, while the side closest to the sun in the middle of the day would be going the slowest speed because it's going backwards relative to the orbital motion, which means it's going roughly Mach 84. So while the average speed of the entire Earth being Mach 86, you're going to a difference of almost Mach 4 every single day. And you say we don't notice it? We would notice it.
Yeah, because we're not affected by the gravity of the sun. We don't feel the gravity of the sun on us. Like we don't feel a pull towards the sun. We can't feel it.
No, I didn't say gravity or gravity pull. I said the actual surface speed of the Earth itself in relation to its speed going around the sun and spinning on its own axis.
Right. So the
One
only way
going 67,000 miles per hour, the other one's going 1,040. It's a bit like the teacup ride. When you're on the outside of the teacup going around the center point, the outside's going much faster than the inside because it's following a smaller circle.
Yeah, we only feel the spin if we're affected by the gravity. So if we're affected by the gravity of the sun, then that change in the Mach, whatever you mentioned from the dark side of the Earth to the light side of the Earth, would affect us. We would feel it. But since there's no change, the only speed we feel is the speed of the Earth and nothing else. The speed of the sun, we feel none of it because the gravity of the sun doesn't.
I didn't even bring in the speed of the sun. I'm just talking about the speed of the Earth. The surface speed of the place you're on is going up and down about Mach 4 every day.
Relative to the sun?
No, just relative to Earth itself. It's got nothing to do with the sun in this particular moment. It's just got to do with the direction.
The speed of the Earth doesn't change. It's continuously spinning at the same speed.
It's spinning at the same speed, but it's also orbiting at a much greater speed.
Orbiting the Earth, orbiting the sun. It's orbiting the sun.
Yeah. So
if we don't feel the gravity of the sun, we will not feel any of the speed from the orbit of the sun.
It's got nothing to do with gravity. Forget the gravity. It's got to do with linear speed, which is orbital speed. Because it's less than 1 degree a day to go 1.6 million miles. It's a linear speed.
We don't feel speed. We don't feel speed. We feel speed relative to gravity. We have to have some force pushing on us. Speed doesn't cause us to feel anything. If we're traveling at 1 billion miles an hour in any direction, we won't feel any difference from being exactly still. Speed is not a force. We don't feel speed.
No, that's crazy because people wouldn't go to amusement parks if we didn't feel speed. Kids wouldn't jump on merry-go-rounds if we didn't feel speed. You know, we feel
those because 100%. They're interacting with a force of gravity and physics.
Exactly, and I'm talking about the forces here. The one force is going 65 times greater one direction than the spin is going, which means that the spin for half the Earth is going backwards relative to that forward speed, while the other side of the planet is going forwards with that speed. So it's accelerating with that speed. The other side is decelerating relative to it. It's all spinning at the same speed, but when you put the two speeds together, one side's accelerating, one's decelerating. It's unavoidable fact.
If there's not the speed, we can't feel speed. So if there's nothing to convert the speed into our bodies, we will not feel it. So there has to be something to convert the speed.
Pass out at great speeds. They hit Mach 4
because
along the back of the head, and
because the speed is converted into our bodies by gravity. So there would need to be some force that could convert the speed into our body. Speed doesn't feel like anything. We need something to make us feel the speed.
So then, therefore, the speed doesn't exist. So therefore, we're on a stationary plane around.
No, speed exists and we don't feel it. Like we're traveling, we can be traveling at 1 million miles in a direction. We'll never feel it.
Just agree that the pilots pass out from it because they do feel it. You agree that children enjoy merry-go-rounds because they do feel it. But you're now saying that when we're going millions of times faster, we don't feel it.
That's crazy. Correct. We do not feel speed. If you're traveling on a train at 1 mile an hour and at 200 miles an hour, it'll feel the same. If you're traveling on a plane at stationary or at 600 miles an hour, it feels the exact same.
You do feel speed.
You don't.
And the thing is, but you're talking about an enclosed capsule once again. Earth is open air. It's open to the vacuum of space.
The open air doesn't matter. Open air doesn't matter.
Just to be sure we can hear you guys, there's a lot of overlap. So just to be sure we can hear, you might go into 2-minute intervals.
So the open air doesn't matter here. Like if we put the entire planet or God put the entire flat Earth on a train and made it go at 1 million miles an hour, you would not feel it. It would feel the exact same as if we were standing still.
It's absolutely ludicrous, mate. Absolutely ludicrous. If you jumped onto the roof of the train going just 60 miles per hour to nearly blast you off, you're talking about going 66,000 miles per hour, mate. That's a huge, massive speed, and you would get blasted into oblivion. You wouldn't even get to a fraction of that speed without feeling it. and everything getting blown off into the vacuum of space.
Yes, because we feel acceleration. We feel the increasing of the speed. We don't feel the speed. We feel the increase or the decrease.
But I've just proven to you that there's a Mach 4 difference every single day.
No.
That's
We
an
don't feel that because again, there's nothing to convert that. No. Acceleration is relative to something converting the speed into our bodies. If it's not converting the speed into our bodies, then we're not accelerating relative to the gravity. So if you don't have acceleration relative to a big force that's like touching you, you don't feel anything.
Again with the gravity. That's the answer to everything, isn't it?
Yes, there has to be something to push you.
But you've misunderstood your own model when you deny the acceleration and deceleration that we'd be going through every day.
What?
You know, it's if you can picture a donut, for example. A donut has got the outer circle and it's got the inner circle. And you know that to travel around the outer circle, you're going a lot faster than to travel around the inner circle. Now, if we considered this donut then as the annual path of the Earth going around the sun, so somewhere in the middle of the hole is the sun, we're going to ignore the fact it's moving 514,000 miles an hour for now, but just assume it's standing still. So the outside ring of that donut is the night time because it's facing away from the sun. The inside part is facing towards the sun. So the much smaller circle is always facing inwards. So technically, in a way, time is going faster on the outside at night time, even though it's not. But the Earth itself is going faster. We measure it the same. You're going with the orbital speed on the outside. So the overall nighttime speed around the sun is exponentially higher than the inner side of the daytime side facing the sun. So that translates to a daily spin every 24 hours of a greater speed moving on the outer circle than the daytime speed moving on the inner circle. Do you understand how it's faster and slower every single day, accelerating, decelerating to map out 365 and a quarter spins around the sun to create the entire donut that it would map out to be?
We can only feel acceleration if it's relative to the big force holding us to the ground, whatever you want to call that. So the sun is a lot farther away, and on your model, it's really, really small. So the force that we feel from the sun is essentially nothing. So our acceleration change relative to the sun is not something we can feel. Doesn't matter what the speed is; it's too far away. It doesn't pull us. Our acceleration to the Earth we feel. So the fact that we don't feel the speed change relative to the orbit of the sun is obvious because we're not being affected by its gravity, or at least by like 1/500th of the amount of the Earth. So it's not something we would feel any more than like being on a train and traveling at 0 miles an hour. Like if it's too far away, we're not going to feel it.
You've totally missed the point, Tom. Like you totally missed it. I'm not talking about the speed of the sun.
Yes, you are. The Earth's orbit around the sun. That's the speed. The acceleration you're talking about is the increase and decrease in acceleration of this
speed is a constant. It's a constant. But the actual rotation means half the world is spinning with the orbital speed, half of it is spinning against it. The Earth. Just the Earth. Forget the sun. Yeah. It's got one direction speed, orbital speed. Forget the sun. We know it's going around that according to your belief, but it's still going that one speed, the constant 66,600 miles per hour. That remains constant.
Yep.
The actual rotation speed remains constant. It's 1,040 miles per hour. So you put one speed together, half the ball is moving with the orbital speed, half is going against it. So the overall speed you're going, it's a bit like if you're spinning the ball, like you said, on the tether, on the moving train, when that ball is going around you, when you're going forwards and the ball is going forwards with you, its overall speed with the train is going faster than when that ball is spinning backwards towards the direction of from the direction of the train. So the overall speed is accelerating and decelerating. If you then say charted an exact picture of the ball moving one direction and spinning around once, it's like making a big loopy spiral sort of thing. It's not making exact same speeds the whole time. It's going much faster with the speed of the train than it is than when it's going against the speed of the train.
So when you're on a train and you throw a baseball, does the baseball go forward slower than when someone throws it back to the back of the train, or does it go the same speed?
More or less, it's because the air is enclosed. It's going to be going pretty much the same speed. What
So
you really
if,
want to do
if
to
the
test that
Earth's
experiment,
orbit, if all of the air in the Earth is going the same speed, then it doesn't matter what the orbit speed is, because it's going to be like the baseball. It's going to be traveling the same speed in both directions.
But once again, the Earth is not enclosed like a train capsule. There is
Yes, it
nothing
is.
enclosing the Earth. There is no reason
Gravity.
for the atmosphere to be moving at whatsoever with the spinning space ball. The spinning
Gravity.
space ball will be moving through the air, not dragging it with it like it's magically velcroed on. We get wind speeds up to 200 miles per hour. They're absolutely devastating. They flatten entire villages, forests, plantations, you name it. Completely devastates everything, flattens it to a T. That's 200 miles per hour. And yet to believe we have perfectly still, calm air is moving 1,000 miles per hour, that's normal. That's ridiculous. Absolutely bollocks, mate.
It's the exact same as having a fan in a car or a fan in a plane. Pretty much all of the air in the plane is pretty much going about the same average speed, but certain areas of it are going faster in one direction than the other. The size of the Earth, those winds, because of the size of the Earth, those winds that you're mentioning are just like turning a fan on in your car. This is not hard. Like the cumulative air on the Earth is going the same speed, which is why we don't feel it.
That's crazy. That makes no sense. No sense whatsoever. That perfectly still air is going 1,000 miles per hour, and yet if some of it slows down by 200 miles per hour, it's devastating. If some of it speeds up another 200 miles per hour, it's devastating. But as long as it finds that Goldilocks zone of moving with the Earth the whole entire time, and yet we see entire storm systems spiraling around as though they're almost perfectly still. It's the winds that are creating the only speed that they feel, that they're also going 10 times faster than the devastating winds that appear to be staying relatively stationary compared to the continents around them. It's ridiculous. It's the same thing with planes flying. Flight would be impossible if Earth was moving any of these speeds whatsoever. You could never land on a north-south facing runway because it'd be moving at a ground speed of 1,000 miles per hour. The plane doesn't go that fast to catch up with that speed to come in at the right diagonal to keep up with it. Everything works because the Earth doesn't move.
Can you throw a baseball on an airplane going 600 miles an hour?
Not very high, not very far. Now, if you go to an open air airplane and you're only going 100 miles per hour and you threw a baseball up, goodbye baseball, it's gone.
Right. So in a closed plane going 600 miles per hour, you can throw a 620 mile per hour baseball.
But what's that got to do with anything?
It's the exact same thing you're saying. Like, oh my God, it's so impossible. Like, you can't possibly throw a baseball 600 miles per hour.
In your model, we're on the outside open air surface of it. There is nothing containing it except the vacuum.
Yeah, there is. So in our model, it's contained by gravity. So you saying, wait. So you saying that,
container.
So what you're saying is that, look at the cumulative speed. Look at the cumulative speed of all these things moving. You obviously can't throw a baseball at 600 miles per hour. So you being on a plane going 600 miles per hour, obviously you'd never be able to throw a baseball, because then it'd be impossible, because then it'd be going 620 miles an hour. Clearly that's impossible. But then guess what? If the air in the container is going at 600 miles per hour, that means you and the baseball are already accelerated to 600 miles per hour. You're only adding a little tiny bit of force to make it go an extra 20. So it's perfectly reasonable to say that you can throw a baseball. It's perfectly reasonable to say that you can throw a baseball going 620 miles an hour, because all of the air around you is already accelerated to 600 miles per hour. The air on the Earth is spinning at the exact same speed the Earth is. Does some of it go in different directions? Yes, just like in the plane, some of the air goes in different directions. When you turn a fan on, it's not very much of it. So just like you can throw a baseball on a plane, we can walk and fly and do stuff on Earth, because the air on the Earth is moving just like it's in a container, because it's contained by a force called gravity.
That is the most ridiculous thing I've ever heard. That's a fantasy belief that your go-to, God-of-the-gaps answer for everything is gravity. That's the equivalent of saying you've got a pressurized tire without having the rubber on it. You just got the rim there, but you just pump enough air around it and you've got a pressurized tire. That's basically what you're claiming, but except at least air has some pressure around it. But in a vacuum, you've got nothing. Everything would go to the path of least resistance, which would dissipate to the vacuum of space, because gravity is not a container. It is nothing. It is empty. Even with, no matter how much gravity you gave to the Earth, you would still lose all your air if it was surrounded by a vacuum, no matter what. You create a vacuum of space on Earth, you have to use great forces, you have to use solid walls to create a vacuum container, and the minute the seal is broken, crack just the slightest, the air instantly rushes to fill the void. Now, if we're in a universe-sized vacuum and you've got no container except a pull of mass in invisible fantasy, pull of mass of something whizzing and hurling through the vacuum, you've got nothing.
Wait,
you've got a balloon without the rubber.
Earlier in our conversation, you said that above Earth, below the firmament, there's no air there, right? It's just, there's nothing, it's empty, kind of like a vacuum tube.
Kind of. It's a pressure gradient. I'd say there's lighter than air gases such as helium and hydrogen and so on.
Right. So there is what we would call space in between us and the firmament somewhere, which means why is there no container there? Because there's clearly like an empty part where there's nothing there, but it's not contained, it's just empty. There's no container in between the very dense part of Earth and the very no dense part below the firmament. So
that's
it
the
seems
beauty
like
of the model.
What?
It's the beauty of the model is that everything finds its place according to the laws of density and buoyancy. So even with or without a firmament, which would be the container, it'd be this upper layer of frozen gases that is cushioned by the atmosphere, by the atmospheric pressure, sitting above everything at this 60, 70 mile height. Even without that, you would still have the same pressure gradient regardless, because the Earth isn't hurtling through a vacuum in the first place. Everything about the heliocentric model is an absolute lie. We don't need it if we're the only physical plane at the bottom of the known universe, going nowhere, not going around the sun. Everything rotates around above us. It's much nearer and closer. The whole outer space dialect debunks itself by claiming that it's a vacuum in the first place. We have a pressure gradient because that is the natural order of things due to density and buoyancy.
All right, so let's take in your model, let's say we just removed the firmament. There's nothing, no water outside. It's just empty, nothingness. Would any of the atmosphere below move?
No, not at all.
So if we just got rid of the firmament, there's no firmament anymore, we could have the exact same atmosphere with no container, just fine.
Well, I wouldn't know because that's not something we could ever experience. But technically speaking, as far as we're concerned, with what we know, according to the laws of density and buoyancy, it wouldn't be necessary. But of course, having it there is what drives the whole entire model, because without the sun, we've got no life, no light. It's pointless without it. So everything works like the organs of the body. Each one is useful and functional because of all the others. So take one away, everything becomes basically useless. So it all works as one thing, and the firmament, I believe, is quite essential to it in the overall scheme of things. But as far as the density and buoyancy of the gases above the stationary planet Earth, they could still just as happily exist without it.
So we don't need a container for air pressure? We do not need a container for air pressure? That's what you're saying?
We need edges, like a lake has edges to hold the water in. There'd be edges of some sort or another eventually. Or if it's an infinite plane, then we've got the same pressure gradient to infinity all around us. But that's just something that we don't know at this stage.
Okay, so if there's no, as long as there's containers on the side, we don't need a container on the top, and you can still have air pressure.
Yeah, that's right. Like you probably heard of how they gas pigs at the slaughterhouses, for example. They drop them down a well shaft filled with a certain gas, which is more dense than oxygen, and they basically kill them humanely that way. Basically, gas still has its own pressure density, pressure gradient. You can see it at sunset, the different layers via the different colors that you can see, the various noble gases that give us daylight and twilight and so on. These things have their own pressure gradient, and once you get above a certain height where there's far less wind and influence from heat and so on, they tend to balance out a lot more equally.
Okay, so if there's no container at the top and we can still have air pressure and it continues to get less and less and less and less to the point where there's no molecules left, what would you call that?
I'd call it the void.
Okay. I'll take it. Void works. I mean, I'd go with space, but I'll take void.
Yeah, but there's a difference though between what we know in reality to exist, because we do have sunlight, we do have starlight, we do know that they need a medium to propagate through for their energy to turn into visible light for us here down at the bottom of the planet Earth. So yes, space exists. I've agreed with that from the start. It's outer space that I am refuting here and say there is no such thing as outer space. The stars and other wandering stars we see, some of them with their moons and so forth, they are not terra firma. They are not big balls of shiny gas. They're not big explosive things, thermonuclear devices, or any of those sorts of things whatsoever. If anything, they're completely sonoluminescence or some other form of energy, some vibratory frequency, which turns into visible light once it hits our firmament and becomes visible light to us through the reactionary process, which is basically a chemical process more than anything.
Okay, so when you say outer space doesn't exist, what do you mean by outer space?
As in the vacuous universe, as in what we see, the stars at night, they are not in outer space.
Well, so you said that there's space exists. What's the difference between space and outer space? Is that like...
Well, the firmament is the difference. We've got the firmament layer, and as I was about to just say before you jumped in, is that many of the ancients, like the ancient Egyptians, for example, called the goddess Nut as the firmament, and the stars are in her. Nearly all the ancient theories about space or the firmament, so to speak, say that the stars are in the firmament. And I put that down to a slight misunderstanding, is that they appear to be in the firmament because that's where they appear as visible light to us. But they could be any distance, arbitrary distance above us. But the fact that they seem to rotate as a single body around Polaris tends to tell me that the visible stars we see are basically a very localized event. As far as whether other galaxies and so forth exist, I think a lot of that is made up hocus pocus done by the agents who gave us heliocentrism in the first place, because we can't actually see them the way that we're shown. And if they are real, then why not? Why not have other heavenly bodies? Why can't there be, seats in heaven that extend forever, for infinity, that once you reach a certain stage of enlightenment, that we star seeds become stars in heaven? And that's what we're looking at when we see the stars.
So by outer space, by outer space, you mean the stars are not there. They're just a illusion. That's kind of what you mean by outer space?
Not at all, no. I believe it's an ether. It's like, if you think of being underwater, I don't know if you've ever had dreams, no doubt you probably did as a teenager, where you're underwater and you're able to breathe when you're underwater. To me, that the ether is similar to that. It's like water, but it's a higher vibrational frequency. Much like we've got vibrational frequencies here on the planar Earth, everything's dense and slow, and everything takes time to manifest. In the higher dimensions, light just manifests instantly, and the ether is kind of like being underwater, but you just bathe in sort of like light and music the whole time, for want of a better way to explain it.
So the stars do exist in the ether outside
Absolutely.
of the firmament?
Absolutely. Oh, yeah.
But it's filled with
higher consciousnesses.
The stars are higher consciousnesses.
Yeah. Raised vibrationary beings. So what we aim to become. Everybody aims to be a star. That's literally comes from that. To become a star in heaven is the goal. So if you're good here on Earth, you do a lot of good, and eventually you might reach enlightenment, and hence you ascend into heaven.
Okay, and why is that more reasonable than saying they're giant balls of gas and rocks?
I mean, just listen to it. Giant balls of gas and rocks, or highly enlightened beings who watch over and rule over our lives. And we've known through astrology all our lives for thousands of years, the influence of the stars and how they affect us, and the way we move through our various lives from karmic consequences and everything. And so when we're born at a particular time, that's how we call it our star's ruling sign. We've got our sun's ruling sign, which is about 50% of our astrological makeup, so to speak. And then you've got the signs of all the various wandering stars, what they're in at your time of your first breath. All of these things are things which, as they say, billionaires pay for astrologers, millionaires don't. So it's one of the most highly sought after sciences, which is ridiculed the lower you are down in the pecking order of things.
Astrology?
Astrology, absolutely.
Well, I mean, if you could demonstrate any like testable predictions with astrology, that would be cool. But as far as I know, they fail every single one of them. So I mean, that would be a great testable prediction that you could use as evidence for your model if you could demonstrate that. I think they've all been proven false, though.
I'm not sure what you mean about predicting what. I mean, we can predict eclipses, can't we? That's ancient astrology. It might have got turned into modern astronomy and astrophysics and all that, but all of this predictive powers are all come from astrology to start with. It's not about predicting certainties. It's about seeing the signs of what's most likely to occur and when's the best time to start a new project, or when it's a good time to mow your lawn, or when it's a good time to plant trees, or it's a good time to pull weeds. It's, that's generally based on the moon signs and whatnot. But astrology is a highly useful tool that we can use to make more successful decisions in our lives, if you know what you're doing.
So like astrology as in the thing that you can read your personality from the stars and your horoscopes kind of stuff, that astrology?
Well, the sun signs, as I said, that accounts for about 50% of a person's makeup on their astrological chart. And so there is general patterns that most people under a certain sun sign will have general personality characteristics, but they're pretty broad, and pretty much that becomes a mentalist's game to be using that alone. Modern astrology is nothing like what ancient astrology used to be, where it's a true science. It's become a bit of a parlor game, really. So no, modern astrology, I don't give it time of day. You can read your chart and say, yeah, whatever. It's a very generalized, broad interpretation, generally speaking, of what sign the moon is in at the time, and it can be somewhat correct. If the moon is in a very fertile sign, and it might say you might come into money, or it's going to rain, or something like that, because it is still a natural occurrence, and the moon and the sign that it's in at the time quite often has a very real effect on the weather, which is why it's so useful for ruling how you run your garden around it.
Yeah. Okay. Well, as soon as you start demonstrating that astrology starts to work at some time, I'm sure you could win a Nobel Prize for that. That would be really cool. But you kind of admitted space was real, and you just said that the stars are spirits, I guess. But I don't see any reason to believe any of this is true. Like we have lots of scientific evidence that they are actually there, that we can literally see them. We can point telescopes at them and see their structure and makeup and see them move. Like we can point, you yourself could buy a telescope in your backyard, look at Jupiter and see the moons of Jupiter spinning.
I could, but I could also draw a completely different conclusion, that they're not moons as such, is that they are children of Jupiter, one of the ancient Greek gods, and that these things, they're part of family, hence they're familiars. And so these things are in adoration of their father figure. They spend their afterlife then in adoration of their father figure, and that's why they appear to be moons going around it. It could just as easily be interpreted that way if you start to see the stars as highly conscious, enlightened beings. And you might see them as balls of gas, but to me that just sounds absolutely ridiculous, because for one thing, for flame, anything to burn, to combust, you need some sort of chemical reaction, such as oxygen or whatever. And generally speaking, the bigger the combustion, the sooner it's over and done with. These things have been there perpetually for thousands of years. There's nothing burning, there's nothing being consumed. It's the same with the sun. And I believe the sun is more like an energy portal into a higher dimension that transfers this energy from a higher dimension, which creates the light that we see as the hotspot apparition in the firmament as the sun, which then simulates the noble gases on the planet Earth to give us daylight. Now, that's a very scientifically proven fact. You can get the various noble gases in test tubes, isolate them, like your krypton, your argon, xenon, neon, and I think there's one other as well. I can't think of them all off the top of my head. You put these test tubes around the Tesla coil, where there's an electromagnetic force coming from it, and they start to glow, and they give us the exact same colors that we see in daylight, the blue sky, the neon colors of sunset and twilight. That's all been scientifically proven, and this is stuff that we flat earth scientists, researchers, have been discovering over the past best part of a decade now. Almost we're getting close to it, and we've been pushing the limits of discoveries. We've come so far in just a short decade of time than what people from thousands of years ago could only have dreamt to being able to do. They didn't have the opportunities of scientific labs. They didn't have modern cameras to be able to send up on helium balloons to see what we actually see, to see that it is as flat for as far as we can see, to see that there's a layer of illuminated blue gas that is our daylight sky. These are things that only the modern scientist has the advantage of. And yet heliocentrism is still based on hundreds of years ago thoughts and philosophies and things that have been, they're all based on superstitious beliefs, like the fact that Polaris disappears at the equator means they think they've descended into the underworld, for crying out loud, that they've gone around a globe. It's a ridiculous notion. It doesn't happen that way. We're just so far away from Polaris that that's where it disappears. And of course, the ancient navigators, they get all superstitious. Oh, we can't see Polaris anymore. We're in the underworld. Oh, God save us, blah, blah.
Pardon my interruption. I'll give you a chance to finish, but did want to mention in just a moment we'll be going into the Q&A. Thanks for your questions, folks. But go ahead, Flat Earth Aussie, if you wanted to draw together some of the threads from this debate, as well as Tom.
Yeah, I actually want to see if I can rehash some of
Flat
Earth Aussie's points.
Yeah, first.
Oh yeah, sure. Go ahead.
Thank you. All I'm saying is that nearly all these beliefs were based on ancient superstitious beliefs because they didn't know any better, and so they just made the most sense of what they had available to them at the time. Charts made in bigger and bigger circles around Polaris because that's where the magnets always pointed towards on their compasses, and you use a compass to make circles, so everything just gets bigger and bigger until suddenly goes pear-shaped because you can't see Polaris anymore. It's all done on ancient superstitious beliefs. All the things of what we call the constellations and everything, they're all different houses of the zodiac. It's all astrology, and it's got mixed up into heliocentrism, which when Copernicus came up with his heliocentric model, he declared that the sun was standing perfectly still, and even he tried to dismiss it, wouldn't believe it. So it's been wrong basically the whole period of history until now. We're finally making more sense of it. We can see much further. We've got telescopes, we've got cameras, we can send things up really high, and we live on a stationary planet Earth, and outer space is a fabrication. NASA has never sent anything to space except your imagination.
Go ahead, Tom.
Yeah, so this was a interesting conversation. I learned a lot of stuff about the Earth I didn't know before, like the fact that the moon is held up by a diamagnetic magnetic field that we can't detect, and it's repulsive, so it pushes the water away, creating the tides when the moon is directly above it, even though it's pushing it away, and that the planets and stars are people, souls, enlightened beings that are in space, that the firmament is 70 miles above us, even though it goes tens of thousands of miles in every direction to get to the size of the Earth, apparently. That we can actually have pressure without a container. You don't actually need the firmament to hold in the gas. We don't need that. And there's actually space between our atmosphere and the firmament where there's nothing. It's just no gas, so it would be like a void space of some kind. Lots of interesting stuff today. The electrolytes. Oh, the electrolytes are affected by the moon's diamagnetic field. That is interesting. Electrolytes don't have a magnetic field. They get not affected by magnetic fields. But that's really cool too. I like that. So there's a lot of interesting things I learned today. But thanks for hosting the debate. I appreciate it, James. Thanks for Flat Earth Aussie. I appreciate you taking the time to have a conversation. You are a pleasant man to talk to. I definitely enjoy your personality a lot more than like Nathan. So thank you for being a nice guy. I appreciate that. And the bird sounds are awesome, by the way. I do love the background bird sounds. But thanks again for having me on. Appreciate it. And let's go to the Q&A.
You got it. Thank you very much, gentlemen. Want to remind you folks, our guests are linked in the description. So if you want to hear more of Tom or Flat Earth Aussie, you certainly can by clicking on their links in the description right now. Let's jump into the Q&A. Thanks so much. Very first one coming in from, you guessed it, Jason Day. Thanks for your question. Said, I love T-Jump. No homo. He is well spoken. Very nice. Sparrow Falls says, Flat Earth Aussie, colloquial usage of terminology doesn't refute scientific principles. Quote unquote, airwaves is colloquial parlance, not science.
Oh, well, that's just what they call it, isn't it? I mean, we call waterways because they're in water. Airwaves is pretty much the term for it, which I think actually is part of, again, going back to astrology. We've come out of the age of Pisces, which is where we conquered waters, and now we've known all the continents as far as we can go to the ice wall. And now we're in the age of Aquarius, which is an air sign, and we are basically conquering the airwaves. We've mastered flight, or we've started some pretty primitive technology of flight, and we send messages through the air all the time. So I think airwaves is as good a term as any.
You got it. And this one coming in from Yudef Hiku. Thank you very much. Says, would a Medicare for all system work on a flat Earth? If so, why don't we have it?
Would a which work?
Would a Medicare for all system work on a flat Earth model? If so, why don't we have it?
Medicare?
Oh, yeah. Here in the U.S., Medicare refers to, let me get a proper definition.
Healthcare.
Yeah, we have they're talking about a medical system of a united one world government for everybody. I think that's the sort of thing most of us want to steer clear of. We'd much prefer to remain as sovereign as possible, not saying it's sovereign citizen movement or anything, but we just want to remain able to make decisions for ourselves. And why not have a united front where we could combine our common wealth that we do have, where it is spread evenly for everybody to have all the medical treatment they need, rather than certain amounts of wealth be distributed, be hoarded by a few individuals who are never going to use it in their entire lives. It should be more equitably spread, absolutely.
You got it, and thank you very much for this question. This one coming in from M2M says, we don't have a pressure against a vacuum of space. We have a pressure gradient. What proves pressure gradients is the countless aircraft flying around the world that measure changes in pressure.
Yeah, I agree there's a pressure gradient. It's exactly the same. If you went underwater, the further deeper you go, the more water is above you pressing down on you. So as you go up higher, you've got less air pressing down on you. That's what pressure comes from. It's just the amount of it. And sea level is where you got the most of it. The higher you get, the less of it is. It doesn't prove we're on a spinning space ball hurtling through a vacuum, which would literally just steal off our entire atmosphere in less than a nanosecond.
You got it. And thank you very much for this question. Do appreciate it. Coming in from Roger Pollock says, flat Earth, please define vacuum, gravity, mass, density, force. I don't know if they mean each of these terms individually or if it's meant to be a single concept.
I think each one of them individually.
I think most of those things are pretty straightforward. We all understand the basics of properties of matter. A vacuum requires a very strong force to create a vacuum state, and to assume that the nothingness of the entire universe isn't a strong force is as ludicrous as saying that you can just make a vacuum inside a giant 24-gallon drum just by going on it or something, sucking it out with your own lungs. You need powerful pumps to create a vacuum state. Just list them one at a time, and I'll happily spray them if it's necessary.
You got it, and thank you very much for this question coming in from Displaced Gamer. Says, explain how we see planets using a telescope.
Well, a telescope is basically similar to a microscope. When you look at something under a microscope, something like, say, a blood cell, for example, you magnify it and make it appear much bigger. So when you're looking at a tiny light in the sky, you're just looking at something with a greater focal length and making it appear bigger to you. It doesn't mean it is bigger, it just makes it visibly bigger. Obviously, it's further away, which helps, but it's not proving that you're seeing terra firma.
You got it. And this one from Made by Jim Bob for T-Jump says, can you isolate gravity in an experiment?
Isolate it? I'm not sure we can do an experiment to identify it and isolate it as the variable in the experiment. Yeah. We can't bottle it, but yeah, we can definitely demonstrate it's the cause of experiments. Sure.
You got it. And this one from Ferran Salas says, what does Flat Earth Aussie think stars are streaming through across the night sky? Is it inside his firmament model and not outside of it?
Well, for one thing, they're not streaming. They're actually moving relatively slowly. Like, it takes almost a full day to rotate around us above us once. And I believe they're in some type of ether, which I say is like a water, but just of a higher vibrational frequency, a much finer sort of substance that's nothing equivalent to water, but we can't explain it. I can't explain it in physical terms because you basically have to experience it to believe it or to understand it. And we can't experience that here on the physical plane, unfortunately.
I got to pee. I'll be back in 1 minute.
You got it. How about this one, Flat Earth Aussie? Going back to this question on the definitions, how about I press you for density? How would you define density per se?
Well, density is basically the amount of mass per volume. So the smaller the volume and the heavier it is, obviously the greater the density of it. That's how you describe density. So you can have, like I like to use a comparison. You got a lead ball and a rubber ball, exactly the same size. You go to a very tall bridge, high bridge, you drop them, and through the density of the medium of air, they will hit the water at exactly the same rate. Now, they're completely different weights, they're completely different densities, but in the medium of air, you've got the same resistance because they're both ball-shaped and air resistance is very minimal. They hit the water, however, the lead ball keeps going down, the rubber ball gets forced back to the surface and it floats. And that just proves that it's the density of the medium that determines the amount of resistance compared relative to the weight upon it. So relative density is the explanation for why things go up or down. And it's the relative of the mass to the medium.
You got it. And this one coming in from Displays Gamer says, how much pressure is the moon adding to the water when it is pushing it? And how come we don't feel this pressure? Math, please.
It's so very little. Some people do go a little bit crazy on a full moon, which tonight we're actually having one, as I explained, and it probably depends on the amount of salt levels in your blood. We are 70% roughly liquid, which is sort of equivalent to the surface of the Earth, but we're so tiny. The amount of pressure from the moon is really, really quite minimal. As I say, it pushes trillions and trillions of tons or megaliters of water around just a couple of meters, which on the scale of the Earth is pretty tiny. You won't feel it. It's like some people saying we don't feel Mach 4 motion because it's too slow. It's too little. This is nothing like a Mach 4 acceleration.
You got it. And Farron Salas says, what does Flat Earth Aussie think stars are? Oh, no, we got that one. Sorry. This one coming in from Displace Gamer says, explain where meteors and meteorites come from, Aussie.
I don't know. I can't claim to know everything. For me, they could be little pieces of rock falling off the moon. They could be from a giant volcanic explosion on some deserted island that got shot so high and coming back down. They could be interdimensional beings coming through portals in their little spaceships and hitting physicality and playing Star Wars with one another and shooting each other up, and we see them as meteoroids. It could be a million different explanations I could make up, but the truth is I don't know.
You got it, and thank you very much for this question. This one coming in from Made by Jim Bob Strikes Again, saying, Tom, can we do proper scientific experimentation in astronomy?
Yes. We do it all the time. Like, one of the best examples is measuring the light that bounces off planets. We can tell what their chemical composition is based on the kinds of waves that bounce off of them.
You got it, and Displaced Gamer strikes yet again, saying, Ozzy, what is the highest point above Earth? Now, what is just past that point? Then what is just past that new point?
I don't really see the point in answering a question like that. As I say, we can send a helium balloon up to about 130,000 feet. That's about the highest we can send anything because it's got such a small payload as the camera. As I say, the firmament maybe 70 miles and everything above the firmament, creating the light effects we see as sparkly stars. There could be any unknown arbitrary height above it that we can never know. But if we can say the firmament is roughly 70 or 60 miles high, then that's pretty much, to our experience, where we see them at, that's how high they are.
You got it, and Displaced Gamer says, how much pressure is... And we got that one. Thanks very much. Don Folman says, can Ozzy explain how GPS works?
Yeah, sure. We got fixed towers everywhere. They're like radio signal towers. And even from way back in World War I days, we were able to ping out signals called radar. And as technology improved over time, we had little computer devices so you could analyze these pings from multiple different towers at once and chart those according to known charts or maps, which we've already designed. And we can fix our location by triangulating off multiple different signals that this little device receives all at once without having to have anything whizzing through the sky whatsoever, which would be useless as far as pinpointing your position anyway. They're fixed ground towers, and that's why it's called Ground Positioning System, GPS.
This one coming in from, do appreciate it, Ozian says, but Brando has what plants crave. It's got electrolytes. I can't remember. Is that from the movie from Trey Parker and Matt Stone? But anyway, Don Folman says, oh, we got that one. The Freak says, I don't discount all that Ozzy has put forth, but I need assurance this isn't a subversion. Please ask Ozzy, what does he say about Jesus of Nazareth, aka Jesus Christ?
I believe that the man existed and he was one of the greatest enlightened masters of his time. And from the age of about 12 or so, or I think it was at 12, he started meeting with various teachers and ended up traveling the whole world, went around India, China, Tibet, all these different places, learning off the great healers, some of the greatest teachers. He was very highly, highly intelligent. So, of course, all the great teachers are always looking for a good student. He even met Gautama Buddha. And when he returned back to Jerusalem, of course, well, that was where he was his native town or native place, where he was now old enough at the age of 33. I believe they have to be able to teach in the synagogue. And he didn't like the way he saw the way the high priests were teaching things. They were exchanging money in the temples of God and so forth. And so he was seen as a bit of a rabble-rouser.
Give us the short version, please. I'm so sorry.
Yeah.
Go ahead.
So he was seen as a bit of a rabble-rouser, and so they had to do away with him. So basically today he'd be called a terrorist.
And DeFreak says, we got that one. Chris Gavin says, Flat Earth Ozzy, a satellite parentheses moon does not increase its speed as it goes around. There is no significant friction that would slow it down.
So say that one again, please. I missed the start.
Gladly. They said, a satellite parentheses moon does not increase its speed as it goes around the Earth. There is no significant friction that would slow it down.
Okay, so that's fine if it doesn't slow down, but something has to increase its speed for it to get back around in front of us, because the orbital speed of the Earth is virtually a linear speed. It's the same thing as I said, sitting on a bike, you got a fly going around you the same speed. Well, the moon doing the same to the Earth has to accelerate to get back around in front in order to fall back around, and it has to slow down then and then speed back up to get around in front again. So there's just no explanation for that. If you're saying there's no friction, it will just fall around us once and keep on disappearing because there's no friction to bring it back again, to slow it down and accelerate it.
Gotcha. And thank you very much for your question. This one coming in from Rudy Questing says, why don't flat earthers ever actually provide a model? It's always, quote, oh, we don't know, but we know it's not this, but we aren't going to show you how that is the case.
Well, that's unfair. He did. Flat Earth Aussie actually presented more of a model than I've ever heard any other flat earther present. So he's actually done that more than anybody else I've ever heard from. So I think props to Flat Earth Aussie for actually presenting what he believes. I think that's a admirable step that most flat earthers don't take.
Yes, thank you, Tom. I believe that's exactly what I did when I described the firmament as being similar to a layer of ice through which we see all these things in a direct line of sight, which is why the sun can appear to be in multiple places at once, because it's not a single thing. So I believe the model itself can only work at full scale, which is why we don't present tiny little models, because they won't work at that scale. They need true scale and perspective to work.
You got it, Ann. Thank you very much for this question. You guys are in danger of becoming friends. You guys are going to be playing Xbox together. Displaced Gamer says, Flat Earth, can you explain what a G-force is?
Well, it's an acceleration force equivalent to 1G, as they call it, which is quite fast. I believe it actually is also 1 Mach, which means 767 miles per hour, the speed of sound. I believe that's what they call a G when it comes to G-force in acceleration.
You got it, and thank you very much for this question coming in from Nobody Here. Says, the Great Lakes has tides and it's fresh water. You said it took salt water for the moon to make tides. How does this mass of fresh water have tides?
As I did say as well, that fresh water does have some amount of dissolved salts in it, electrolytes, and the Great Lakes, being a very huge body of water, has a very, very slight tide. I think it's equivalent of about 5 centimetres as opposed to about 2 metres on oceanic tides. So it's slightly salty. All water has some amount of electrolytes in it. So if you've got a very, very big body with a certain amount of, the more the water evaporates out of it, the higher the salt content will gradually increase over hundreds of years. So it's probably slightly more salty than most other freshwater lakes.
You got it. This one coming in from Alexander says, Ozzy, how does your model account for north and south celestial poles at the same time? How does your model make predictions on eclipses?
Well, first of all predictions of eclipses are done through centuries and centuries of observations. And so we can predict them like clockwork. We've got the Antikythera device, which is thousands of years old, and it's predicted from a geostationary model so accurately that it can even predict the shade of red or orange that the moon will turn during an eclipse. So these sort of things have been known from a geostationary model for a very, very long time. As far as the celestial poles are concerned, that is again a matter of perspective. If you're in a big room with a disco ball in it, for example, if you look directly at the disco ball and you look at the lights above it, they appear to be going one direction. But if you turn your back and look at the lights going on the wall, they're still going the same direction, but from your perspective now, they appear to be going the opposite way. And I don't see the stars here in Australia going around a celestial pole as such. I see the Southern Cross in the southeast virtually every night in the same position almost, and by the morning, by the time it's too bright to see it again, it is far in the west, which means they're still going the same direction around Polaris. We're just seeing it in a much bigger circle further out from beyond the equator.
You got it. This one coming in from D.D. Murley's. D.D. Murley says, Ozzy, why do you not understand the physics of this stuff? My guess is you disagree.
All the physics remain exactly the same as we've observed them since millennia, since forever. Physics don't change just because we understand that the ground itself isn't moving. If anything, they make far, far more sense. And the idea of curving water around a ball, which then has continents below that water level, that's, to me, utter insanity. The laws of physics make far more sense on the planar Earth.
This one coming from Chris Gammon says, please define speed.
Motion.
Next, Chris Gammon and Dee Dee Murley both ask, would you please define acceleration?
Well, change of speed, like increase of speed from a particular point. So you're standing still and you start walking and then you start running, well, then you're accelerating. That's pretty straightforward, I think.
Then they both ask, please define velocity.
Velocity is just motion. Whether you're accelerating or decelerating, you still have a velocity if you're moving.
And Chris Gammon also says, blindfold yourself in a car and detect the speed of the car while blindfolded. I'll wait.
That's actually quite fun to do. I once did that many years back in the back of somebody's ute. These days, you'd get huge fines if you got busted doing that. But we went for a big trip out west one night, and I laid, because there wasn't a lot of seats in the front, it was just a ute, which means you got 3 seats at the most. There was 4 of us, so we took turns laying in the back, and it was quite a pleasant experience actually laying in the back with your eyes shut. And you could feel the motion, of course, but you don't sort of feel it in the same way you would with a visual experience of, say, driving through a tunnel, where the experience of seeing lights going past you would tell you you're moving. It's actually, it's you only feel it when you got the wind in your face, basically.
You got it, and thank you very much for this question. Coming in from Bernie Sharp says, given an object in motion will remain in motion unless acted on. Why, if I lift a bowling ball up in a vacuum chamber, it doesn't continue moving up?
Well, exactly, because the upward force is applied by his muscular system. He is applying the force. If he left it sitting down on the ground, it would stay at ground, but he's applied a force. And then if you remove the resistance, take your hand out from it, then it has the reaction to it and drops again. It's ridiculous to think it would keep going up in a place that has zero resistance, which is what a vacuum is.
You got it. Thank you very much for this question coming in from Made by Jimbo. Says, Tom, is gravity a scientific theory? If so, what's the observation, experiment, and all three variables, please? U beta. I made that last part up, but go ahead.
There's tons of different scientific experiments of gravity. The LIGO experiment, the one that Einstein did measuring the curvature of light around the sun. There's a whole bunch of them. It's not easy. It's not hard to think of them. The three variables, the independent variable, the dependent variable, and the whatever. Just Google it yourself.
This one coming in from Git Stanfield says, has Ozzy ever questioned physicists about his concerns, meaning how they know how fast the Earth is orbiting around the sun, for instance? Has he gone on physics forums to find out how it's measured?
I've been on Quora, or however you pronounce it. I call it Quora, Quora, quite a bit, asking questions in all sorts of different forums, or mostly responding to questions, and then, of course, debating with people. And it seems to me that nobody actually, just like Einstein, actually has any method for detecting any motion of Earth whatsoever. They just have to call it all relative, which to me, you've got two types of speeds. You've got real speed and you've got non-speed. And relative speed is in the section of non-speed. Real speed and non-speed. Relative is just hogwash. It's made up as an excuse for why you can't detect real speed.
You got it. Juicy. Wolf von Hinslick, thanks for your question, says, look, have you ever driven in your car with a soda and the air conditioning running? The soda is perfectly still, and some parts of the air are moving faster. It's really that simple.
It's another non sequitur argument. There's no windscreen to the Earth. If you've ever driven in a car, like it happened to me once, where I did get into a little fender bender with a tree, and I was able to put my little Suzuki into four-wheel drive and get out of there and drive it home. And if I hit about 45 kilometres an hour, the wind streaming in my face, because the windscreen got knocked out, big star in it from my head, forgot to have my seatbelt on too. Every time the wind got about into my face, I couldn't see. It was too much. And that's 45 kilometres an hour. So you're talking about a windscreenless Earth going thousands upon thousands of miles per hour, and you don't feel a damn thing. I tell you, you won't be able to see a thing. You ride a motorbike without goggles or glasses on and you hit 60 kilometres an hour, you won't see very well. You need some sort of eye protection. So to think that we could do it on an open air Earth without a windscreen is ludicrous.
You got it, and thank you very much for this question coming in from, you guessed it, Displaced Gamer strikes yet again, says, how does the sun stay in the sky? Is it less dense than the atmosphere? If not, how is it floating?
Well, in my opinion, the sun is what I call an interdimensional portal, and it's above the firmament. So it's in the ether in the first place. It's not even affected by the laws of density and buoyancy. It's in a completely different realm altogether. And whatever forces that keep it going, obviously it's still going around Polaris. Now, Polaris obviously has some very important role as to how everything rotates around it, being magnetic north, but I don't know what that is exactly. But there are some mysteries we don't know, but we can still, a bit like with gravity, we can still tell you what the effects of it are, even if we don't know what it is.
You got it. And Derek Donner, thanks for your question, says, what keeps me from falling through the ground on a flat earth model? What keeps my more dense bones from falling through my less dense flesh?
It's called the properties of matter. And as we know, solids are solids, liquids are liquids, and gas are gas. And they pretty well behave themselves reasonably well within the realms of their own particular densities. Like if your bones were made out of lead, they might have a greater chance of crushing your flesh and going through you or something, but bones are actually quite light. It's a really silly question, really. It's everything is density and buoyancy, and relative density takes care of everything. everything is worked out perfectly fine to work exactly the way it does.
You got it, and thank you very much for this question. While I read these questions, we do have more. I want to remind you folks, both Tom and Flat Earth Aussie are linked in the description. They have their own YouTube channels. So if you want to hear more, I mean, hey, the links are waiting right there. And that includes on our podcast, folks. We have them linked in the description there as well. Get Stanfield, appreciate your question, says, T-Jump, duh, stars are obviously light projections on the firmament. I thought you'd know that.
It's not just that, they're souls. They're magical souls that higher enlightened beings that are trapped in orbit around each other.
Flat Earth Aussie, I think they're making fun of you.
Yeah, I wouldn't say that they're trapped. I'd say that they've earned their seat in heaven, and they're in absolute paradise and in absolute bliss. Like, I've had a couple of near-death experiences myself where I've been out of body for a while, and when you go to this realm, the pleasant state of being is something you do not want to ever leave. And I've heard of cases where drug addicts have had an overdose, and when they get brought back, they get violently angry. They say, why the hell did you bring me back? Because this place, when you get there, is absolutely beautiful, blissful, and pleasant. And you come back here and it's like you're in living hell again.
Did you say that you've been to heaven? I've never heard you say this. We've known you for this whole time, and you just didn't mention that, oh, I've been to heaven, by the way. You never told us this?
It's not something that's ever come up in conversation, actually, but I've been there several times, actually. At least 3 times that I can count. And
well,
the first time when I did it,
like,
I was only like 11, and I kept trying to get back there as often as I possibly could. I'd go back to the place where it happened. It was amazing, and I could never find this portal back through to it. But I didn't even know what I was searching for until years later when I realised what it was.
Well, we didn't know it was like going to the grocery store for you. And Tyler Cates, thanks for your question, says, appreciate it. Says, great job, James and crew. Appreciate it. And all street cred to T-Jump and Flat Earth Aussie, who are indeed linked in the description. And Bubblegum Gun says, conspiracy ran by CIA to discredit real conspiracies. Oh, Flamio says, if space is fake, where is heaven? And oh, we got that. Did we read this one? If space is fake, where is heaven and where does Yahweh live? Is that the one that prompted you?
That one.
Is that the one that prompted you to tell us that you've been to heaven like hundreds of times? They said, if space is fake, where is heaven and where does Yahweh live?
No, I said I might have experienced going to another dimension 3 times, which was absolutely blissful. I don't know if it's actually heaven. I believe there's multiple levels of dimensions that we are capable of experiencing, and I would think that the one that we think of as heaven is probably just the next one above. I reckon there's probably multiple different levels higher in life than you get. But as far as Yahweh is concerned, I don't believe there is an actual being as such. What people like to think of as God, whatever name. There's multiple gods that are just higher in life than masters, which we can appeal to as teachers, which is why the Egyptians had hundreds of gods. Yahweh is just one, and really I'm not so sure he's one of the better ones, to be honest. And where he exists, I think, is mostly in the realms of the imagination, just like outer space.
Experience in prebiotic chemistry says, hey, Tom, I can tell that your brain hurts after this debate. Do you need some Vicodin? Just kidding, YouTube. Nobody's offering controlled substances. Tom, if you want to respond, you may.
I'm sad. Why aren't you offering controlled substances?
This one coming in from Perf says, Flat Earth Aussie, do you have an explanation for planetary retrograde that works on your model? Because it works perfectly with ours.
Absolutely, yeah. The wandering stars, they move independently. They are like lesser gods in a sense, you know, as the Greeks recognize. They're known by their various names, and they actually do move. If you plot out their patterns that they move in throughout the year and the years, decades, and so forth, they move in sacred geometric patterns. And so, of course, when you're moving in a spiral, sometimes it would appear retrograde, other times moving forwards. It doesn't mean that we're the ones moving. It just means that they're the ones moving independently to the rest of the stars, which we see moving in the same fixed sidereal motion.
You got it, and thanks for this one. Coming in from George R. says, Flat Earth Aussie, are you now or have you ever been a reptilian?
No, I don't believe so.
Does reptilian mean... Go ahead.
Apparently my mother used to take a bit of pride in being called the Dragon Lady or something, but I think that's something that it was a bit of an ongoing joke. But no, I'm
Juicy.
100% no reptile blood in me.
Does okay, so reptilian means you are a reptile, not that you believe in them. Well, that's another topic we can have in case you believe in reptiles.
They're hybrids or something. They're hybrids, and they've got like brainwave patterns that they can use to manipulate themselves into making them appear to you as though they're a human being. But sometimes those waves get a bit weak, and you see their true reptile form come through. Sometimes just in their eyes with the slits. Other times you see their full reptilian form. But yeah, they're shapeshifters in that they manipulate how they appear to you telepathically somehow.
Should have known. This one coming in from Design Song 1 says, T-Jump Aussie said diamagnetic was, quote, anti-gravity, unquote. Why did you not nail him?
Well, I think by anti-gravity, he means repulsive instead of attractive. I don't think he means literally anti-gravity. I don't think he meant the word as being literally a force of anti-gravity. It's just a slip of the tongue. So just catching him on a slip of the tongue isn't like a main point.
You got
I'm
it.
not totally against the use of the word gravity, like it still has some sort of definition, which if you understand the Latin word, which I brought up in the introduction, comes from the word gravis or gravitas. That's where we get the word gravity, and it only means weight. So it still has some application if you want to use that word.
This one coming in from Perf. Did I read this? Flat Earth Aussie, do you have an explanation for planetary retrograde that works on your... Oh, we got that. Sorry about that. This one coming in from Made by Jim Bob says, Tom, I challenge you to a debate on this channel. You affirm astronomy is science and one single experiment that demonstrates gravity.
Okay. Pay me $50. I'll do any debate.
We love nothing more than when person does a public call out. So thanks for that, Made by Jim Bob. And Design Song 1 says, oh, we got that one. Chad Martin says, Flat Earth Aussie, what's your opinion on Inner Earth Agartha?
Yeah, I've done a lot of research into that as well. That's part of where my journey began, probably over 30 years ago when I was reading about Hollow Earth concepts. And I've got no doubt whatsoever that there are other realms deep within the Earth. I mean, we've even got DUMBs, which are these deep underground military bases, and these things are massive as well. These are man-made ones, so I don't see why they couldn't have been over all the millions and millions of years that humans and reptilians and all that have existed on the Earth. There can't be other places that they've gone to for whatever reason deep underground. Agartha is just as possible as any other Hollow Earth theory, really.
You got it, and thanks very much for your question. This one coming in from Bubblegum Gun says, Flat Earth Aussie, do you think that Jeff Bezos faked his space trip?
They didn't fake anything. That they didn't go very high. They didn't go. I don't know much about the Bezos one. I think you sort of called him. I heard about the Virgin Galactic dude. He went about 50 miles. I think these other ones went about 60 miles, and that's I think about the maximum that any man-made thrusting object can possibly reach. And the air just gets too undense, for a better word, too void of physicality for any sort of vehicle to move through it with the propulsion methods that we currently use. It's just not possible to go any higher than that. And in the overall scheme of things, 60 miles is barely the lacquer layer on a classroom globe. It's nothing. It's not space.
You got it, and the logical hillbilly says, I've been to heaven once. Her name was Maria Maria. Next up, Chad Martin, thanks for your question, says, it reminds me when, I can't remember the character's name, Walter Matthau is singing in Grumpier Old Men, one of my favorite movies. Next, Chad Martin says, shout out to Made by Jim Bob. Next up, Design Song 1 says, T-Jump, when he goes on about ludicrous speeds, the slam is always relative to what? Yes, a fly on a rocket flies ludicrously to someone. Why not nail him?
Because he doesn't believe in relative speed. So if you say relative, he's just going to say, that's a made-up word. So trying to actually explain it to him. I don't know what the best way to explain how speed is. relative to some force that can actually cause the speed. That's why I tried to do that in the debate. He did not get it.
Juicy. And this one coming in from M2M says, altimeters debunk the whole notion of a pressure against a vacuum. It's a gradient of pressure from 14.7 pounds per square inch from MSL to almost nothing above 80 kilometers.
Altimeter.
It measures altitude according to the pressure of the air above it. So obviously it would decrease exponentially as you got higher. So it would give you actually a false reading, which is why I think that the methods we use to measure height are actually hugely inaccurate. Same as I say, using radio waves to measure distance in height is highly inaccurate as opposed to measuring distance on the ground, which is quite accurate.
You got it. This one coming in from Putafoot. Thanks for your question. It says, question for Flat Earth Aussie. You said that the moon was made on Earth. Who made it?
I don't know exactly who, but as far as I'm concerned, it would have taken some people of some great size. And with all the readings I've done, especially to do with Agatha and all the other things, is I do believe, and there's much evidence for it. We've had a debate yesterday about the existence of giants. And I've also heard things about a certain being who was sentenced to Earth, deep down inside the Earth, who was able to bioengineer certain beings of some great massive things. So in short, giants.
You got it. And with that, we do want to say thanks so much, folks. I'm going to be right back with updates on future juicy debates such as this one and many others. You don't want to miss it. So stick around and I'll be back in a moment. But I want to give a huge thank you to T-Jump and Flat Earth Aussie for this civil, fascinating discussion. It's been a true pleasure. Flat Earth Aussie and T-Jump, thanks so much for being with us tonight.
Thanks, guys. See you later.
Yeah, thanks you so much, Tom, and thanks, James.